Hello, you're listening to Night Cosmos Sleep, where even the smallest traces in nature can open the door to vast stories about Earth and the universe. In the southern French Alps, among ancient sediment layers along the Drauze River, researchers discovered the remains of pine trees that once lived in a world very different from the one we know today. When those trees still stood on the mountainsides, Earth was only beginning to emerge from the last ice age. Large regions of land were still covered in ice, and most of the civilizations familiar to us had not yet appeared. From the outside, nothing about those trunks suggested that they had witnessed an extraordinary event. They were not scorched, they carried no signs of an impact, and there were no large cracks telling the story of a disaster. But when scientists separated the extremely thin annual growth rings and measured the carbon preserved within them, they found an unusual signal. In one ring formed about 14,300 years ago, the proportion of carbon-14 rose suddenly, as though Earth's atmosphere had briefly received a dose of radiation far greater than normal. The source of that signal did not come from the soil, the water, or the tree itself. It began beyond Earth, with an exceptionally powerful burst of energetic particles released by the sun. Those invisible particles crossed the space between the two worlds, collided with the atmosphere, altered part of the atomic composition of the air, and were eventually absorbed by the tree and locked inside the newly formed wood. The people living at that time left behind no instruments, images, or written records of the event. Yet a small tree quietly preserved its trace for more than 14 millennia. And from a thin line almost impossible to distinguish with the naked eye, scientists began to realize that the sun may once have produced an event more powerful than anything modern instruments have directly observed. To understand how an event in space could remain preserved inside wood, we first need to look more closely at the way a tree turns each year of its life into a physical layer of memory. When we look at a cross-section of a tree trunk, we usually see a series of circles layered one inside another. Some lines are lighter, some darker, some rings are broad, and others are so thin that they almost blend into the wood beside them. They may look like simple natural markings drawn around the center of the trunk, but each one is actually the remains of a growing season that has already ended. From one year to the next, a tree does not record time with numbers. It records time through the new cells formed within its own body. In temperate regions, where winter and summer differ clearly from one another, the rhythm of tree growth often follows changes in the weather. When spring returns, temperatures begin to rise, frozen ground thaws, and water starts moving more freely through the roots. Daylight lasts a little longer each day, allowing new leaves to open and photosynthesis to become more active. Inside the trunk, a thin layer of tissue just beneath the bark, known as the vascular cambium, begins producing new cells. At the beginning of the growing season, a tree usually needs to transport large amounts of water from its roots to its branches and leaves. For this reason, the wood cells formed during this period often have relatively large internal spaces and thinner cell walls. This wood appears lighter in color and is sometimes called early wood. As summer passes, growing conditions gradually change. Water may become less available, the days begin to shorten, and the tree prepares to enter a slower phase. Cells formed later in the season are usually smaller, with thicker walls, creating a darker band of wood. The transition from the light early wood to the darker late wood forms one complete growth ring. When the cold season arrives, wood production nearly stops. The following spring, the tree begins forming another layer outside the old one. The boundary between the late wood of the previous year and the early wood of the new year becomes distinct, allowing each year of the tree's life to remain preserved as a ring encircling the trunk. In this way, a tree trunk can become a natural clock. A tree that lives for 100 years will often contain close to 100 growth rings, although in practice, counting them is not always as simple as looking at a set of perfect circles. During some years, a tree grows very little, producing a ring so narrow that it is difficult to distinguish. Some trees may form rings that do not fully encircle the trunk, while injuries, disease, insects, and local environmental conditions can make the wood structure more complicated. For this reason, scientists do not simply cut down a tree and count the lines from the center outward. They often remove narrow wood cores using a specialized tool, allowing them to study the internal structure without necessarily felling the tree. Each core preserves a sequence of growth rings extending from the wood near the bark back through layers formed decades or even centuries earlier. The width of each ring can reflect part of the environment the tree experienced. During a warm year with sufficient water, a tree may grow strongly and produce a relatively wide ring. During a cold or dry year, or one with a short growing season, the ring may be narrower. However, this relationship is not identical everywhere. A tree growing near the cold upper limit of a mountain forest may respond strongly to temperature, while a tree in an arid region may be more sensitive to rainfall and soil moisture. The tree's age, the type of soil, elevation, sunlight, competition from nearby trees, and even injuries from the past can all influence the way a growth ring forms. A wide ring, therefore, does not simply mean that the year was favorable in every way, just as a narrow ring does not necessarily prove that the entire region experienced a disaster. To reconstruct climate history, researchers must compare many trees, remove the influence of age, and account for the particular growing conditions at each location. But in the story of the ancient solar storm, the most important feature is not whether the ring was wide or narrow. The trace that scientists discovered was not a special shape visible to the naked eye. It lay deeper, within the atomic composition of the wood formed during one particular year. Before reaching those atoms, scientists first need to know exactly when the layer of wood under study was formed. This is the task of dendrochronology, the science of tree ring dating, which uses patterns of growth to build timelines extending across many generations of trees. If researchers examine only one dead tree, they may be able to count its rings and determine how many years it lived. But they may not know the exact year in which the outermost ring formed, especially if the bark and youngest wood have been lost. A trunk may contain 200 rings, but without knowing when the tree died, the sequence is still like a calendar from which all the year labels have been removed. To solve this problem, scientists compare patterns of wide and narrow rings among many trees. Imagine that a region experienced a distinctive sequence of years. Several dry years in a row, followed by one wetter year, and then 2 more years of poor growth. That pattern could create a recognizable sequence of ring widths. Trees growing in the same region during the same period often preserve similar patterns, even if the exact width of each ring differs from one tree to another. A living tree may provide a sequence extending from the present back several hundred years. A wooden beam taken from an old building may contain rings that overlap with the early part of that living tree sequence, while also reaching farther into the past. A trunk discovered in a bog, riverbed, or sediment layer may overlap with the timber from the old building and extend the timeline even farther back. Each time researchers find a matching pattern, they can join 2 tree ring sequences together. This process is usually called cross-dating. It does not rely on one ring alone, but on a longer pattern, much like joining 2 sections of a musical composition by recognizing the same sequence of rhythms in both. Through repeated connections of this kind, tree ring chronologies can extend across thousands of years. In some regions, tree ring records have created continuous timelines reaching far into the past, providing science with one of its most precise systems for dating organic material. Unlike many methods that provide only an estimated range, tree rings can place a piece of wood within a specific calendar year, as long as its sequence is securely connected to the modern calendar. However, not every ancient tree can be immediately attached to a known chronology. Some forests existed so long ago that a gap remains between them and younger trees, with no overlapping sample yet found. In such cases, scientists may clearly determine the order of hundreds of rings within the ancient group. They know which rings came earlier and which came later, and they understand how the lifespans of different trees overlapped, but they still cannot say with certainty which calendar year marked the beginning of the sequence. A sequence like this is called a floating chronology. It is like a strip of film that preserves the correct order of every frame, but has lost its date label. A viewer can tell which scene came first and which followed, but cannot yet determine the exact year in which the sequence occurred. For the ancient pine trunks preserved in southern France, this problem was especially important. Their rings could be assembled into a relative sequence showing that the trees grew during the same period near the end of the last ice age. But to assign each ring to an exact calendar date, researchers needed additional independent anchor points. An anchor can come from radiocarbon dating, from a volcanic ash layer with a known age, or from chemical changes that appeared at the same time in several types of natural material. And sometimes, an event beyond Earth can create the clearest marker of all. If a burst of energetic particles from the sun causes atmospheric carbon-14 levels to rise sharply for a short period, trees growing across many parts of Earth may preserve the same change. A carbon-14 spike found in one growth ring can be compared with a similar signal in securely dated tree ring chronologies or in other natural archives. When that match is confirmed, the solar signal becomes a pin in time. It fastens the floating tree ring sequence to the correct place on the calendar, turning a relative order into a moment that can be identified by a specific year. This creates a remarkable connection. The tree preserves a trace of the sun, and that trace helps humanity determine exactly when the tree lived. An event occurring about 150 million kilometers from Earth becomes a marker for the history of an ancient forest, while the forest itself preserves evidence of the activity of the star that once illuminated it. Yet within every growth ring, there is more than the familiar form of carbon that makes up much of living matter. Hidden among countless stable atoms is a very small proportion of another form of carbon, created high in the atmosphere and gradually changing over time. This rare form of carbon carries its own radioactive clock, while also preserving the traces of energetic particles that once arrived from space. Inside every tree ring are countless carbon atoms that once drifted through the air before becoming part of the trunk. Most of them are carbon-12, the most common and stable form of carbon in nature. A smaller portion is carbon-13, which is also stable but slightly heavier. And alongside those two familiar forms is carbon-14, far rarer, yet especially important for reading the past. All three are carbon. The difference lies only in the tiny structure of the atomic nucleus. Carbon-14 contains more neutrons, which means it does not remain stable forever. Over time, it decays slowly, decreasing according to a measurable rhythm. After about 5,730 years, half of the original carbon-14 remains. Because of this property, it becomes a natural clock preserved in wood, bone, seeds, and other materials that were once part of a living organism. While a tree is alive, it continually absorbs carbon dioxide from the air to build its leaves, branches, roots, and new layers of wood. The proportion of carbon-14 inside the tree therefore reflects the proportion present in the atmosphere. But when the tree dies, this exchange stops. No new carbon enters the trunk, while the carbon-14 already inside continues to decay. By measuring how much remains, scientists can estimate how much time has passed since the tree stopped living. However, this clock does not begin inside the tree. Carbon-14 is first created high in the atmosphere, where energetic particles from space are constantly arriving at Earth. Under normal conditions, our planet is always surrounded by a faint flow of energetic particles. When those particles enter the atmosphere, they collide with atoms in the air and trigger a series of reactions. Some of these reactions release neutrons. Those neutrons can then interact with nitrogen-14, the most common form of nitrogen in the atmosphere, transforming part of it into carbon-14. The entire process is invisible. No light is carved directly into the tree trunk, and no stream of material travels straight from space into the wood. Carbon-14 is simply a product created by the atmosphere after it receives energetic particles from beyond Earth. Once formed, carbon-14 combines with oxygen and becomes part of carbon dioxide. That gas gradually mixes through the atmosphere, is carried around the planet by winds, exchanges with the oceans, and enters the living world. Trees absorb it through their leaves during photosynthesis, then incorporate the carbon into the wood that is forming. Each tree ring therefore records more than 1 year of growth. It also preserves a very small sample of the atmosphere's composition during that period. The carbon atoms within the wood once drifted through the air, passed through the leaves, and were then locked inside the trunk when the growing season ended. Most of the time, the amount of carbon-14 being produced changes fairly slowly. The flow of particles entering the atmosphere may rise or fall, but ordinary variations usually do not create a dramatic jump in tree rings. As a result, successive layers of wood generally contain carbon-14 levels that change relatively gradually. But if the sun suddenly releases an exceptionally large burst of energetic particles toward Earth, that familiar rhythm can be disrupted. More particles enter the atmosphere, more neutrons are produced, and the amount of carbon-14 rises. Some of that newly formed carbon then mixes into the air, is absorbed by trees, and remains preserved in the wood produced during that year. What scientists found in the ancient pine trunks was not a direct trace of light or heat. It was a very small shift in the proportion of atoms, created by the atmosphere and then preserved by the trees. In this way, an event that once occurred in space could remain quietly stored in wood for thousands of years. Under ordinary conditions, carbon-14 production is relatively steady. For that reason, when carbon-14 levels suddenly rise sharply within a single tree ring, it indicates that the atmosphere experienced something very different from a normal year. And in the ancient pine trunks of southern France, that change appeared as a distinct spike rising above the surrounding timeline. When the ancient pine trunks were removed from the sediment beside the Drauset River, the first thing the researchers saw was still only wood, darkened surfaces, grain that had endured thousands of years, and growth rings lying close together within a structure that seemed completely still. Nothing visible on the trunks directly revealed that a major event had once passed through Earth's atmosphere. The most important trace began to appear only when the individual rings were separated and taken into the laboratory. The work required patience. Each ring corresponded to a period of growth, so the boundaries between them had to be identified carefully before the wood could be divided into extremely small samples. The samples were then cleaned to reduce the influence of soil, water, and other substances that had entered the trunks during the long period in which they remained buried. The remaining material was processed so that its carbon could be measured by instruments sensitive enough to detect an extraordinarily small amount of carbon-14 among a vast quantity of ordinary carbon. The result did not appear as an image of the sun or as a mark that could be seen directly. It appeared as numbers, with each value representing the proportion of carbon-14 within a particular growth ring. When those values were arranged in chronological order, they formed a record of change extending across many years. Throughout most of the data sequence, the line shifted gently. Some sections rose, while others declined, but the changes usually occurred slowly and did not stand out sharply from the surrounding years. This was consistent with the way carbon-14 is normally produced and then distributed through the atmosphere, oceans, and living world. But at one point in the tree ring sequence, that familiar rhythm was suddenly broken. The proportion of carbon-14 rose clearly over a very short period, forming a sharp spike within an otherwise relatively smooth line of data. The signal did not disappear immediately afterward. Instead, it gradually declined over the following years as the newly formed carbon mixed with the rest of the atmosphere and continued moving into the oceans, soil, and living organisms. The shape of the signal suggested that it was not the result of a slow environmental change. A process lasting several decades or centuries would usually leave behind a broader curve. The carbon-14 spike in the ancient pine rings, by contrast, began rapidly, as though the atmosphere had received a large additional flow of energetic particles within a short period of time. Even so, finding a sharp spike was not enough to conclude that the sun had produced an enormous storm. In science, an unusual signal must first be tested before it can be connected to a specific cause. Researchers needed to make certain that the change truly belonged to the tree rather than being the result of preservation, sample preparation, or a small error in measurement. A growth ring could also be identified incorrectly if its boundary was too faint or if part of the trunk had been damaged. When working with wood more than 14,000 years old, missing even a single ring could place the entire signal in the wrong position on the timeline. The samples, therefore, had to be compared with one another, measured again, and checked across different sections of wood. Even after the carbon-14 spike had been confirmed, its origin was not entirely clear. High-energy particles do not come only from the sun. Space beyond the solar system continually sends cosmic rays toward Earth, and under unusual circumstances, a powerful distant phenomenon might also be considered as another possible source of radiation. Earth's carbon cycle made the story more complicated as well. Once carbon-14 is created, it does not immediately enter a tree trunk. It mixes through the atmosphere, exchanges with the oceans, and spreads through many parts of the biosphere. Changes in the way carbon moves between these reservoirs can sometimes raise or lower the proportion measured in trees, even when the original production of carbon-14 has not changed very much. Rather than reaching for an immediate answer, scientists examined each possibility in turn. They evaluated the accuracy of the tree ring sequence, repeated the measurements, compared multiple samples, and used models to estimate how much carbon-14 had been produced in the atmosphere. Explanations that did not fit were gradually eliminated, leaving a narrower and narrower group of possible causes. The process was not like a secret being revealed all at once. It was more like watching an image slowly come into focus. At first, there was only an unusual point in the data. Then that point was confirmed by additional measurements. Next, its shape and magnitude were compared with known events. Finally, the possibility of an exceptionally powerful flow of energetic particles from the sun gradually emerged as the most consistent explanation. But a single tree, no matter how precisely it is measured, remains an archive from one location. The ancient pines of southern France absorbed carbon from the atmosphere around them, and part of the signal could have been influenced by regional conditions. To determine how far the event had truly extended, researchers needed another form of evidence preserved through an entirely different process. Far from the mountain slopes where the pines once grew, snow fell over Greenland season after season and was compressed into thick layers of ice. Within that ice, the atmosphere also left traces of energetic particles that had once passed through Earth. If the signal found in the French tree rings could also be identified in that distant place, the sharp spike in the wood would no longer be only the story of an ancient forest. It would become the trace of an event that had once affected the entire planet. Leaving behind the darkened pine trunks of southern France, the search for traces of the ancient event continued in an entirely different place. In Greenland, snow had fallen through thousands of winters, covering the surface with thin white layers that were gradually buried beneath new snowfall. Over time, the weight above compressed the snow crystals together, transforming them into ice and creating a natural archive extending far into the past. To reach those ancient layers, researchers drilled deep below the surface and extracted long cylinders of ice. From the outside, they looked like little more than transparent or cloudy white columns, but within them lay the accumulated record of countless seasons. Every layer had begun as falling snow, carrying with it dust, sea salt, and tiny substances that were present in the atmosphere at the time. In younger sections of ice, seasonal boundaries may still be relatively clear. But deeper below, pressure compresses the older layers and makes them thinner, causing the task of identifying individual years to become increasingly difficult. Scientists must rely on many different clues, including chemical composition, dust levels, and patterns of snowfall accumulation to construct a timeline for the ice they are studying. Among the traces preserved, there is beryllium-10, a rare isotope produced in the atmosphere. Like carbon-14, it can form when high-energy particles from space enter Earth's atmosphere and collide with atoms in the air. Once created, beryllium-10 attaches itself to extremely small particles suspended in the atmosphere and is gradually carried down to the surface by rain or snow. In Greenland, some of the beryllium-10 fell with the snow and became trapped as that snow turned into ice. Ice cores can therefore preserve changes in the abundance of this isotope across many different periods. When the flow of energetic particles entering the atmosphere increases, the amount of beryllium-10 being produced may also rise, leaving behind a chemical signal in the ice layers that form afterward. However, this signal is not identical to carbon-14 in tree rings. Carbon-14 becomes part of carbon dioxide, circulates through the atmosphere, and is then absorbed by trees during photosynthesis. Beryllium-10 attaches to tiny particles and settles to the surface with rain or snow. The two isotopes are created through related processes, but they follow different paths before becoming preserved in nature. This difference makes comparing them especially valuable. If a carbon-14 spike appeared in only one tree, there would still be a possibility that it had been influenced by local conditions, the way the tree grew, or a small error during measurement. But when a signal from the same period is also found in Greenland ice, an explanation based on a minor event around one ancient forest becomes much harder to support. The pine trees absorbed carbon from the air in southern France, while Greenland snow received particles settling onto a distant region in the far north. The two archives were separated by thousands of kilometers and formed through different mechanisms. Even so, both indicate that the atmosphere passed through an unusual period at approximately the same time. This agreement does not mean that each ice layer and each tree ring could be aligned perfectly from the beginning. Ice accumulates at different rates from one region to another, and material in the atmosphere also requires time to travel and settle. Scientists therefore had to account for uncertainties within each chronology, as well as possible delays between the moment an isotope was produced and the moment it became preserved in wood or ice. But even after those uncertainties were considered, the evidence from the two sources remained consistent with the same major event. Carbon-14 increased in the tree rings, while beryllium-10 also became more abundant in the ice record. Both isotopes are products of reactions that occur when the atmosphere receives a larger than normal flow of high-energy particles. This reduced the possibility that the carbon-14 spike resulted only from a local change in the carbon cycle. A change in forests, soil, or oceans might alter the amount of carbon entering trees, but it would be difficult for such a process to create a corresponding beryllium-10 signal in distant ice at the same time. The presence of both traces suggests that the cause likely began high in the atmosphere before its effects were distributed across different parts of the planet. The ice core therefore became an independent witness. It did not tell the story through wood or photosynthesis, but through tiny particles that had fallen with the snow. If a tree ring is like a page of a calendar written inside a trunk, then an ice core is a different collection of records, arranged layer by layer beneath Greenland's surface. When both archives preserve the same unusual change, the mystery no longer belongs to one ancient forest alone. From this agreement, the hypothesis of an exceptionally powerful energetic particle event became more convincing. A large flow of particles entered the atmosphere, increasing the production of carbon-14 and beryllium-10 over a relatively short period. Afterward, each isotope continued along its own path. Some of the carbon entered trees, while the beryllium settled into the ice. Thousands of years later, those two journeys met again in the laboratory. Dark brown growth rings and frozen columns of ice pointed toward a moment lost from all human memory. They could not tell us what color the sky had been that day, nor could they describe the shape of the event on the sun. But together, they confirmed that Earth's atmosphere had once received an unusually large flow of energetic particles. The trace had now taken on a planetary scale. Yet trees and ice preserved only what happened after the particles reached Earth. Their source still lay about 150 million kilometers away, on a star that appears almost unchanging when viewed from the ground. To understand what could release such a powerful stream of particles, we must return to the Sun and look more deeply into the restless layers of matter moving beneath its familiar light. From Earth, the Sun often appears as a bright disk that hardly changes. Each day, it rises, crosses the sky, and disappears below the horizon in such a steady rhythm that it is easy to imagine this star as permanently stable. Yet behind that familiar light lies a world in constant motion, where hot matter, electric charges, and magnetic fields continually interact. The Sun does not have a solid surface like Earth. Most of its matter exists as plasma, a state in which the temperature is so high that atoms can no longer retain their ordinary structure. Electrons separate from atomic nuclei, creating a sea of electrically charged particles in continuous motion. Because the matter carries electric charge, every flow within the Sun can generate and reshape magnetic fields. These motions unfold across many different scales. Hotter material rises from below, cools, and then sinks again, creating enormous currents of convection. At the same time, the entire Sun rotates around its axis, but not like a rigid sphere. The region near the equator completes a rotation faster than the areas close to the poles. Over time, this difference stretches, bends, and winds the magnetic field lines around the star. We can imagine the magnetic field as a collection of invisible cords extending through and above the glowing material. As different parts of the Sun move at different speeds, those cords gradually become twisted. Most of the time, they change slowly and retain their overall structure. But in certain regions, the twisting becomes more complicated, allowing increasing amounts of energy to build within the magnetic field. Regions like these are often associated with active areas on the Sun. Sometimes they appear as dark patches known as sunspots. These spots are not truly dark when viewed on their own. They simply have lower temperatures than the bright regions around them, which makes them appear darker by comparison. They usually form where powerful magnetic fields pass through the Sun's visible surface. A single sunspot does not necessarily indicate that a major eruption is about to occur, but groups of sunspots with complex magnetic structures can become places where energy accumulates over many days. Above them, magnetic field lines extend into enormous arcs filled with hot plasma, connecting regions where the magnetic fields point in different directions. As these structures continue to stretch and twist, they may eventually become unable to maintain their previous arrangement. Magnetic field lines can break apart and reconnect in a new configuration. This process of magnetic reconnection releases some of the stored energy, sometimes within a very short period. Several different phenomena may emerge from the same active region, but each one carries energy away from the Sun through a different path. One of these phenomena is a solar flare. This is a sudden increase in radiation emitted from a region of the Sun. Within minutes, that area may brighten dramatically in X-rays, ultraviolet light, and many other wavelengths. Radiation travels at the speed of light, so when a flare occurs on the side of the Sun facing Earth, its signal reaches our planet in only about 8 minutes. Earth's upper atmosphere absorbs most of these dangerous forms of radiation, so people on the ground do not feel the flare directly. However, the ionosphere can change almost immediately, disrupting certain forms of radio communication. This is Earth's fastest response to an event on the Sun, because light arrives before most of the material that may also be ejected. Another phenomenon is a coronal mass ejection. Instead of releasing only radiation, the Sun may send an enormous cloud of plasma and magnetic field outward into space. This mass of material leaves the Sun's outer atmosphere and expands through the solar system. Depending on its speed and direction, it may take roughly 1 to several days to reach the region of Earth's orbit. Not every coronal mass ejection travels toward our planet. Many plasma clouds move into other parts of the solar system and have little significant effect on Earth. Even when one reaches us, its impact depends on the direction of the magnetic field carried within it. If that magnetic structure connects favorably with Earth's magnetic field, a large amount of energy can enter the space environment surrounding the planet and create a geomagnetic storm. Geomagnetic storms can make auroras brighter, expand them toward lower latitudes than usual, and disturb technological systems. But the strength of a geomagnetic storm cannot be determined solely from the brightness of the solar flare that came before it. A powerful flare may not be accompanied by a plasma cloud directed toward Earth, while a less visually dramatic eruption may still carry a magnetic structure capable of producing major effects. Along with radiation and vast clouds of plasma, the Sun can also accelerate protons, electrons, and other particles to extremely high energies. The fastest of these particles do not travel together with the entire ejected cloud. They may be accelerated near the site of the flare or by the shock wave formed as a powerful eruption moves through the surrounding solar atmosphere. Once accelerated, these particles travel along magnetic field lines stretching through interplanetary space. If the magnetic configuration connects the eruption region with the area near Earth, part of the particle stream may arrive in only a few tens of minutes or several hours. Slower particles continue arriving over a longer period, keeping radiation levels around the planet elevated. This is the type of phenomenon most directly connected to the traces found in tree rings. When protons with sufficient energy enter the atmosphere, they trigger chains of collisions that increase the production of carbon-14. A tree ring does not record the brightness of a flare in the way a telescope observes visible or invisible light, nor does it reveal exactly how large the plasma cloud was. What remains preserved in the wood mainly reflects the amount of energetic particles that entered the atmosphere and created new isotopes. These three phenomena can often occur close together because they arise from changes within the Sun's magnetic field. An active region may produce a flare, launch a cloud of plasma, and accelerate a stream of energetic particles at the same time. Yet they are not three identical parts that always accompany a single event in the same way. A flare may be extremely bright, while the particle stream reaching Earth remains relatively weak. A coronal mass ejection may produce a powerful geomagnetic storm without leaving a distinct carbon-14 spike. There may also be significant energetic particle events whose initial light signatures are not equally remarkable. This distinction is important when looking back at the event that occurred more than 14,000 years ago. From tree rings and ice cores, scientists can infer that Earth's atmosphere received an exceptionally large amount of energetic particles. But those natural records do not preserve every aspect of the eruption. They cannot reveal exactly how bright the flare became, what shape the plasma cloud took, or how powerful the resulting geomagnetic storm may have been on Earth. The clearest surviving evidence is the trace of the particles themselves. They left the Sun, crossed the immense space between the two worlds, and reached the layer of air surrounding our planet. There, their energy was transferred into countless small collisions, changing part of the atmosphere's atomic composition before the signal entered trees and ice. To create such a large carbon-14 spike, the Sun needed to do more than simply release energy. It also had to transfer part of that energy into protons and electrons moving fast enough to cross space, reach Earth, and penetrate deeply into the atmosphere. The journey of that invisible particle stream is the next part of the story, beginning within the Sun's turbulent magnetic fields and ending in tiny reactions between the atoms of the air. When a region of the Sun's magnetic field suddenly releases energy, not everything leaves the star in the same way. The light from a solar flare travels fastest, crossing the distance between the Sun and Earth in just over 8 minutes. A large cloud of plasma usually moves much more slowly and may take anywhere from about 1 to several days to reach the region of Earth's orbit. Between those two timescales are electrically charged particles accelerated to extremely high speeds, with protons often making up the most important part of the flow. Protons are among the fundamental components of matter. Under ordinary conditions, they remain inside atomic nuclei. But on the Sun, where plasma is constantly moving and magnetic fields can store enormous amounts of energy, some protons are pulled from their surroundings and driven outward at high speed. When the number of such particles rises sharply, the phenomenon is known as a solar energetic particle event, or more broadly, a solar radiation storm. That name can easily suggest an image of a sheet of burning fire sweeping across space, but what actually happens is far quieter and much more difficult to see. There is no single wall of flame rushing toward Earth. Instead, countless protons, electrons, and some heavier particles move through space, each carrying its own amount of energy and not necessarily arriving at the same time. Some particles may be accelerated close to the region where the flare occurs, as the magnetic field rapidly rearranges itself. During this process, magnetic energy is transferred to electrically charged particles, causing them to accelerate dramatically. Other particles may gain energy from the shock wave created by a coronal mass ejection. As a large plasma cloud races away from the sun at high speed, it compresses the environment ahead of it and forms a shock region capable of continuing to accelerate particles across a great distance. Because the particles are produced through several mechanisms and carry a wide range of energies, they do not reach Earth as a single group. The fastest protons may arrive near the planet within a few tens of minutes or several hours. Slower particles appear later and may keep the radiation environment around Earth elevated for many hours, or even longer. This means that a solar event often reaches Earth in several stages. First comes the light from the flare. Next may come the fast stream of energetic particles. Finally, if a coronal mass ejection is directed toward the planet, the larger cloud of plasma and magnetic field arrives. These three stages may be connected to the same active region, but they do not occur at the same time and do not produce the same kinds of effects. The journey of the protons is not simply a straight line from the sun to Earth. The space between the two worlds is not completely empty. The sun continuously releases a thin stream of plasma known as the solar wind, carrying the star's magnetic field throughout the solar system. Because the sun rotates, these magnetic field lines are bent into broad curves, forming a slowly spiraling structure across space. Charged protons tend to travel along these magnetic field lines. Their ability to reach the region near Earth therefore depends not only on the power of the eruption, but also on how the active region on the sun is magnetically connected to the planet through interplanetary space. Some eruptions are extremely powerful, yet most of their particles are guided in another direction. By contrast, an event occurring in a favorably connected location can send particles toward Earth quite rapidly. As the particles approach the planet, they encounter the magnetosphere, the region of space controlled mainly by Earth's magnetic field. The magnetosphere acts like an enormous protective layer surrounding the planet, deflecting most charged particles from the solar wind and radiation events. Because of this protection, Earth's surface does not directly receive the full stream of particles moving through space. However, the magnetosphere is not a completely sealed wall. Its shape and magnetic orientation make it easier for some particles to enter near the polar regions. There, magnetic field lines point downward toward the atmosphere, creating natural pathways that guide some protons and electrons deeper into the air. When high-energy protons enter the upper atmosphere, they begin colliding with nitrogen, oxygen, and other atoms. A single proton is far too small for a person to feel, but it can carry enough energy to trigger a chain of reactions. The first collision produces secondary particles, which continue moving downward, striking other atoms and creating additional collisions. Most of the particle stream's energy is absorbed in the upper layers of the atmosphere. This is why people standing on the ground do not see protons falling like rain or feel a sudden wave of heat arriving from space. The thick atmosphere above has already slowed and dispersed most of the energy before it can reach the surface. Yet even though humans cannot see the particles, the collisions still leave changes behind. They increase ionization in certain layers of the atmosphere, meaning that more atoms and molecules lose electrons than usual. This can alter the way radio waves travel, especially near the polar regions where particles enter more easily. At high altitudes, satellites and spacecraft may also be exposed to a stronger radiation environment. High-energy protons can penetrate some shielding materials, interfere with electronics, or gradually damage components over time. For astronauts beyond the atmosphere's thick protective cover, the same particle stream presents a much greater danger than it does to people standing on Earth's surface. The most important trace in this story, however, was not preserved in machinery, because when the ancient event occurred, humanity had no satellites or electrical grids. What remained after more than 14,000 years were the small reactions that took place within the atmosphere. When a sufficiently powerful flow of protons enters the air, the collision cascades they create produce additional neutrons. Those neutrons then interact with nitrogen-14 and form carbon-14. Some of this newly created carbon later combines with oxygen, mixes through the atmosphere, and is absorbed by trees during the growing seasons that follow. Beryllium-10 is also produced through similar chains of reactions. It then attaches to tiny particles and settles to the surface with rain or snow. In this way, the same particle storm can leave traces along two different paths. Carbon-14 remains in tree rings, while beryllium-10 is preserved in distant layers of ice. The rain of protons was therefore almost invisible to anyone living on the ground, but it did not pass without leaving evidence. It changed part of the atmosphere's chemistry, and those changes were gradually transferred into wood, ice, and other natural archives. Even so, observing a large carbon-14 spike does not directly reveal how many protons reached Earth. The tree ring signal also depends on the way carbon moves through the atmosphere, whether the trees were actively growing at the time, how much carbon was absorbed by the oceans, and many other conditions on the planet during that period. The world more than 14,000 years ago was not exactly the same as it is today. The climate was colder, ice covered a larger area, and the composition of the atmosphere also differed in certain ways. Newly created carbon would have moved through a system that was not identical to the modern carbon cycle. To determine how large the ancient event truly was, scientists therefore cannot look only at the height of a sharp spike in the tree rings. They must reconstruct the journey of carbon from the moment it was created high in the atmosphere until it became preserved in wood, while also recreating the atmosphere of an Earth that was still emerging from the last ice age. When the data from the ancient pine trunks is placed beside events known from more recent periods, one detail immediately stands out. The carbon-14 spike around 12,350 BCE is nearly twice as high as the spike recorded around the year 775. Looking at that difference, it is easy to reach the simple conclusion that the ancient storm must have been twice as powerful. But a tree ring is not an instrument that directly measures the number of protons that left the sun. The signal preserved within it is the final result of a long journey through Earth's atmosphere, climate, and planetary carbon cycle. To understand this more clearly, we can begin with a single carbon-14 atom newly created high in the atmosphere. It appears after an energetic particle enters Earth, triggers a cascade of collisions, and transforms part of the nitrogen into carbon. But from that moment until the new atom becomes preserved inside a tree trunk, it still has a very long distance to travel. First, it must combine with oxygen and become part of a carbon dioxide molecule. The air mass carrying it continues moving through the atmosphere and may drift across many latitudes before descending into the lower layers. Some of the carbon is absorbed by the oceans, some enters the soil, and another portion is taken up by plants through photosynthesis. Every stage can dilute the original signal, delay it, or distribute it unevenly across different regions. The height of a spike in a tree ring therefore depends on more than the amount of carbon-14 that was created. It also depends on where that carbon traveled, how long it took to reach the lower atmosphere, and how much of it the tree absorbed during its growing season. Earth's magnetic field is one of the first factors that must be considered. The magnetic field surrounding the planet deflects many charged particles arriving from space. When the field is stronger, it can prevent more particles from reaching the atmosphere. When it is weaker, more particles may penetrate deeper and produce additional isotopes. That magnetic field does not remain unchanged across thousands of years. Its strength and shape shift gradually as material moves within Earth's core. The same stream of particles from the Sun can therefore produce different amounts of carbon-14 if it arrives during two periods when the magnetic field is not the same. A large spike in tree rings may sometimes reflect not only the power of the solar event, but also the level of protection the planet had at the time. Climate also affects the path carbon follows. Around 14,300 years ago, Earth was still colder than it is today, and was undergoing major changes as it emerged from the last ice age. Wind patterns, the exchange of air between atmospheric layers, and the rate at which carbon circulated were not necessarily the same as they are in the modern world. Carbon-14 is produced mainly in the upper atmosphere, while trees absorb carbon dioxide near the ground. Between those two regions lies an entire system of complex motion. Air must be mixed, transported downward, and distributed between different areas. If this transport happens quickly, the signal may enter trees sooner and in a more concentrated form. If it happens more slowly, the newly created carbon may pass through several seasons before being fully absorbed. The concentration of carbon dioxide in the atmosphere also makes a difference. When the total amount of carbon dioxide is lower, a newly created quantity of carbon-14 can represent a larger fraction of the atmosphere's carbon reservoir. This can make the spike measured in trees appear higher, even if the number of carbon-14 atoms produced did not increase by the same proportion. Near the end of the Ice Age, atmospheric carbon dioxide levels were lower than they are today. Newly formed carbon-14 was therefore mixed into a smaller carbon reservoir. This is one reason the spike preserved in the ancient pine rings may appear more prominent than one produced by a similar event in the modern atmosphere. The time of year is also very important. Trees do not absorb carbon at the same rate throughout all 12 months. In temperate regions, most new wood forms during spring and summer when temperature, water, and sunlight are more favorable. During winter, growth slows dramatically or nearly stops. If a solar particle event occurs just before the growing season begins, the newly created carbon-14 may appear clearly in that year's ring. If it occurs when the tree has almost stopped growing, part of the signal may not appear until the following year's ring. The same amount of carbon produced at different times of year can therefore create differently shaped spikes in a tree ring sequence. Along with the atmosphere in the growing season, the oceans form an enormous carbon reservoir. The sea surface continually exchanges carbon dioxide with the air. Some newly created carbon dissolves into the water and is then carried downward by ocean currents. Marine organisms also absorb carbon and move it into the food web. On land, trees, soils, and other organisms retain part of the carbon as well. The entire system operates like many connected reservoirs. Carbon continually moves from the atmosphere into the oceans, from the air into plants, and then returns through respiration and decomposition. The spike preserved by a single tree is therefore only one part of a signal that has traveled through this vast network. This is why scientists cannot simply look at the percentage increase in carbon-14 and multiply it directly to calculate the storm's strength. A spike twice as high does not necessarily mean the proton flow was exactly twice as powerful. Before producing an estimate, researchers must separate the effects of the magnetic field, climate, atmospheric carbon dioxide levels, the growing season, and the exchange of carbon among different reservoirs. To do this, researchers use a model called SOCOL:14CX. The name may sound complicated, but its central idea is fairly simple. The model creates a scaled-down version of Earth's atmosphere and carbon cycle inside a computer, then follows the movement of carbon-14 through that system. In the simulation, carbon-14 is produced at different altitudes after an energetic particle event. From there, winds carry it through the atmosphere, it mixes between different layers, and it gradually moves downward toward the surface. Some enters the oceans, some enters the biosphere, and some remains in the air long enough to be absorbed by trees. The model can also alter climate and magnetic field conditions to better match Earth more than 14,000 years ago. Instead of assuming the planet was identical to the world of today, researchers include a colder climate, lower carbon dioxide levels, and a different magnetic field strength. They then adjust the size of the particle event until the simulated result produces a carbon-14 spike similar to the one measured in the tree rings. At the center of this entire process remains the image of a newly created carbon atom finding its way through Earth's enormous system. It begins high in the atmosphere, formed during a collision lasting only an instant. It may then drift through several layers of air, enter a cold air mass, descend toward the surface, and finally be absorbed by a leaf. In the end, it becomes part of a thin layer of wood growing inside the trunk. Other atoms may follow entirely different paths. Some enter the ocean. Some remain in the atmosphere longer. Some do not enter a tree until 1 or 2 seasons later. This dispersal is what makes the signal preserved in wood different from the original amount of carbon produced. When all these factors are considered together, the picture begins to change. Although the ancient carbon-14 spike is nearly twice as high as the one around the year 775, the particle flow that produced it was not necessarily twice as strong. Conditions on Earth at the time made the signal appear more prominent within the tree rings. The modeling results indicate that the event around 12,350 BCE was still more powerful than any similar event identified so far, but the difference was not as great as a direct comparison of the two spike heights might suggest. This does not make the event any less extraordinary. Instead, it places its scale on a more cautious and accurate foundation. Through this process, tree rings reveal more than the fact that something unusual occurred. The shape of the spike, how quickly it rose, and the way it gradually declined over the following years also contain information about when the carbon was created and how it entered the growing season. Once climate, the magnetic field, and the carbon cycle are reconstructed within the model, the trace in the wood begins to reveal more than the storm's magnitude. It also allows scientists to narrow down the period during which the event may have occurred, bringing an event from more than 14,000 years ago close to a particular season of the year. Throughout much of natural history, events from the distant past can be placed only within broad spans of time. Scientists may determine that a tree lived thousands of years ago, that a layer of ice formed during a particular period, or that a climatic shift occurred near the end of the Ice Age. But bringing an ancient event close to a particular season of the year is far more difficult. With the carbon-14 spike discovered in the ancient pine trunks, the shape of the signal allowed researchers to take another step. By simulating how newly created carbon moved through the atmosphere and entered the tree rings, they found that the event most likely occurred during the early months of 12,350 BCE. The range consistent with the evidence extended from the beginning of January to the end of April, while the result that most closely matched the tree ring data fell around early March. This does not mean that scientists have identified an exact calendar date. No written record survives from that time, and no observational instrument captured the moment when the sun began sending its stream of particles toward Earth. The early spring interval is a probability-based conclusion, inferred from the way the signal appeared across consecutive growth rings and from the movement of carbon through the atmosphere. To understand how a season can leave such a trace, we need to return to the journey of carbon-14. Immediately after energetic particles collide with the atmosphere, the newly created carbon does not travel directly into a tree. It forms mainly at high altitudes, then combines with oxygen, and gradually becomes part of atmospheric carbon dioxide. From there, air currents must carry it downward, mix it with the carbon already present, and bring it into regions where plants can absorb it. This process takes time. Part of the signal may move downward relatively quickly, while another portion remains in the atmosphere longer, continuing to drift between regions before entering the oceans, soil, or living organisms. The moment carbon-14 is created, and the moment it appears clearly within a tree ring are therefore not exactly the same. Trees in the northern hemisphere also do not grow evenly throughout the year. During the cold months, growth slows dramatically. The cambium becomes almost dormant, leaves are less active, and the amount of carbon entering the trunk decreases. When spring returns, temperatures rise, water begins moving from the roots into the branches, and the tree starts producing a new layer of wood. If an energetic particle event occurs early in the year, the newly created carbon-14 may require some time to descend from the upper atmosphere toward the surface. By the time the tree enters its growing season, part of that carbon may already be available for absorption and incorporation into the developing ring. The signal can therefore appear quite clearly within the wood formed during the same year. If the event occurs later, when the growing season is already well underway or nearing its end, the new carbon may not enter the trunk in large amounts soon enough. In that case, the stronger part of the signal may not appear until the following year's ring. The way the carbon is divided between two consecutive rings can therefore preserve a faint clue to when the event began. Researchers compared the carbon-14 proportion in the year of the spike with the years immediately before and after it. They examined not only the maximum height of the signal, but also how quickly it appeared and how it declined. The model was then run using many different hypothetical dates throughout the year. Each proposed date produced a slightly different distribution of carbon across the growing seasons. When the event was placed too early, the simulated carbon entered the tree rings in a pattern that did not fully match the actual data. When it was placed too late, too much of the signal shifted into the following year. The interval from January through April produced a better match, with early March emerging as the most likely point. Even this result, however, must be treated cautiously. The ancient trees no longer exist to tell us exactly when their growing season began. The climate near the end of the Ice Age differed from today's, so the growth rhythm of those pine forests may not have been identical to that of modern forests in the same region. Atmospheric circulation, carbon dioxide levels, and the rate at which carbon entered the biosphere can all be reconstructed only approximately. Early March should therefore be understood as the center of a range of possibilities, not as a firmly established date. Science does not always find one exact moment, but it can still narrow the past from centuries to only a few months. That alone reveals how much more information can be held within a tree ring than its simple appearance might suggest. With the time interval narrowed, the ancient event begins to feel more immediate. We can imagine a day in early spring more than 14 millennia ago. Snow may still have covered the higher ground, while lower slopes began feeling the first changes of the new season. The trees were preparing to emerge from dormancy, though their new layers of wood may not yet have fully begun to form. The people living then inhabited a very different world, moving through landscapes without cities, roads, or electric light. They had no way of knowing that a stream of protons from the sun was crossing the space between two worlds. To the naked eye, the bright disk in the sky may not have looked very different from the days before. Above them, however, the story was unfolding in an entirely different way. The fastest particles entered the region near Earth, encountered the magnetosphere, and were guided toward more accessible parts of the atmosphere. Collisions began, neutrons were created, and an unusually large amount of carbon-14 gradually appeared in the air. No sound descended from the upper atmosphere to the ground. No wave of fire swept through the forest, and no burn mark appeared immediately on the tree trunks. The change occurred at the atomic level, far too small for anyone living at the time to recognize. But during the weeks and months that followed, the newly created carbon began mixing through the atmosphere, moving downward and entering the cycles of life. As the growing season opened, the pine trees absorbed carbon dioxide through their leaves. Along with the ordinary carbon came a proportion of carbon-14 far higher than in the preceding years. Those atoms entered sugars, cellulose, and the new wood gradually thickening around the trunks. By the time the growing season ended, the signal had been preserved within a thin ring of wood. The tree did not know that this layer was different. It simply continued living through the seasons that followed, adding more rings around the outside. The trace of the particle event was gradually buried deeper within the trunk. Eventually, the tree fell, was covered by sediment, and remained still for thousands of years. Because of the way carbon was divided between consecutive rings, a small part of that ancient spring can still be recognized. Not through color, temperature, or sound, but through the timing of a rare isotope's appearance. From a few slices of wood, scientists can bring an unwitnessed event back to a period lasting only a few months. But the spring of 12,350 BCE did not unfold on an Earth like the one we know today. Vast ice sheets still covered large regions of the northern hemisphere. Sea levels were lower, and the climate was shifting after an extended period of cold. The people who experienced that rain of particles lived in a world emerging from the Ice Age, where forests, rivers, and coastlines all had shapes different from those familiar to us now. In the early spring of 12,350 BCE, the sun still shone upon Earth from its familiar distance. Day and night continued to alternate, and the seasons still followed one another, but the planet below was not the world we inhabit today. Many regions remained deeply shaped by the Ice Age. Vast ice sheets still covered broad areas of the northern hemisphere, and the global climate was colder than it is now. That world was changing, but it had not yet fully entered the more stable conditions of the millennia that followed. Ice was beginning to retreat in many places, meltwater was returning to the oceans, and ecosystems were gradually expanding into regions that had once been too cold. Yet the imprint of the Ice Age remained clearly visible in the landscape, the climate, and the way carbon moved among the atmosphere, soil, oceans, and living organisms. A large portion of Earth's water was still locked within continental ice sheets. As a result, sea level was lower than it is today. Many areas that now lie beneath the ocean were still dry land, connecting regions that would later be separated by water. Coastlines lay far from their familiar modern positions, rivers crossed broader plains, and natural corridors allowed humans and animals to move between lands that are no longer connected. The atmosphere also had a slightly different composition. Carbon dioxide levels were much lower than they are in the modern era. This was not only related to the colder climate, but also affected the way newly created carbon-14 mixed into the atmosphere after an energetic particle event. When the total amount of carbon dioxide was smaller, the carbon-14 produced by such an event could form a more noticeable proportion of the atmosphere's carbon reservoir. For this reason, the carbon-14 spike in the ancient pine trunks cannot be interpreted as though it formed within the atmosphere of today. The newly created carbon had to move through a world with different temperatures, different amounts of ice, different oceans, and a carbon exchange rhythm that was not entirely the same as the modern one. These conditions did not alter the nature of the event on the Sun, but they did influence the way its final signal became preserved in the tree rings. In the southern Alps, the landscape was also being reshaped by major climatic changes. Ice that had once covered large parts of the mountains had retreated from some valleys, leaving behind rock, sediment, and newly formed waterways. Wherever conditions became suitable, pine trees began growing across mountain slopes and lower areas of land. Those forests were not necessarily as extensive or stable as modern forests. They may have expanded during periods of relatively favorable climate and then declined again as temperature and moisture changed. Each tree lived through many seasons, adding another growth ring and preserving a small part of the atmosphere's composition from each year. Some trees eventually fell near streams and rivers. Their trunks were carried a short distance by the water or came to rest within damp sediment. Where oxygen was limited and burial occurred quickly enough, decomposition slowed. The wood did not become completely petrified, but neither did it decay as exposed trunks normally would on the surface. Over thousands of years, layers of soil and gravel continued accumulating above them. The pine trunks that had once stood within a cold landscape gradually became part of the ground beneath it. They were not preserved because they contained an unusual signal, and nothing suggested that humans would one day discover them. It was simply a rare combination of where the trees fell, the movement of water, the sediment, and the local chemistry that allowed the wood to survive for so long. Meanwhile, the world above continued changing. The ice retreated farther, sea level rose, and forests expanded before shifting again with the climate. Generations of people moved through the landscape, leaving behind stone tools, traces of hunting, and temporary shelters. But no written language recorded an event on the Sun, and there was no way to measure radiation or observe conditions in space. The people living at that time may have noticed changes in the sky if the event was accompanied by bright auroras or some other visible phenomenon. But even if they witnessed something unusual, the memory could only have survived through spoken stories shared among small groups. Over many generations, such a story might have changed, blended with others, or disappeared completely. If the energetic particle event produced no obvious sign at ground level, perhaps no one knew it had happened at all. Protons crossing space did not form a visible flame. Newly created carbon-14 did not change the color of leaves or make tree trunks glow. To someone living beneath the atmosphere, that day may not have seemed very different from an ordinary day in early spring. This marks a major difference between the ancient world and the present. Today, a powerful event on the sun can be detected by many telescopes. Satellites can measure X-rays, count energetic particles, and observe clouds of plasma leaving the star. Forecasting centers can issue warnings to astronauts, airlines, satellite operators, and electrical grid managers. Around 14,300 years ago, no such systems existed. There were no satellites to experience interference, no radio communications to be disrupted, and no electrical grids to reflect disturbances in Earth's magnetic field. The world was less vulnerable to space weather, but it was also almost entirely unable to recognize its cause. The most enduring memory of the event was therefore not preserved in human stories. It remained within reactions that took place high in the atmosphere, where the flow of energetic particles produced additional carbon-14 and beryllium-10. Afterward, each isotope followed a different path. Some entered trees, while some fell with the snow and became preserved in ice. The ancient pine rings did not preserve images of the landscape. They do not reveal where people were or what they may have seen, but they retained part of the air the trees once absorbed. In the layer of wood formed after the event, the proportion of carbon-14 had changed, and that change survived longer than any footprint or spoken account from the time. There is a particular stillness in the way the past was preserved. A storm began on the sun, crossed the space between two worlds, and altered the chemistry of Earth's atmosphere. On the ground, trees continued drawing up water, opening their leaves, and producing new wood just as they had in previous seasons. At no moment did a tree recognize that part of the star's violent activity had entered its trunk. By the time the tree fell, the signal had already been locked inside. Newer layers of wood had grown around it, sediment later covered the entire trunk, and the climate continued to change. More than 14 millennia later, when the wood was brought back into the light and measured in a laboratory, the ancient chemical reaction finally became a story that could be read. The world near the end of the Ice Age left us no photograph of the day the particle storm arrived. Only indirect traces remain, clear enough to confirm that the event occurred, but not complete enough to reconstruct the entire scene. No journal tells us what the sun looked like that day, and no observer described the color of the sky. For this reason, when we try to imagine what ancient people may have witnessed, science must preserve a careful distance between what has been measured and what can only be inferred. Carbon-14 tells us that an enormous stream of particles entered the atmosphere, but by itself, it cannot recreate the sky of that distant day. From ancient tree rings and layers of ice, scientists can determine that an enormous flow of energetic particles once entered Earth's atmosphere. The carbon-14 signal shows that the event far exceeded ordinary variations, while beryllium-10 preserved in the ice helps confirm that it was not merely a local change. Yet, even though the evidence is clear enough to prove that an extremely powerful event occurred, it still cannot fully recreate the sky of that distant day. Carbon-14 mainly preserves information about the amount of energetic particles that entered the atmosphere. It does not reveal exactly how bright the solar flare was, how large the accompanying plasma cloud became, or how the magnetic field inside that cloud was oriented as it approached Earth. These details would have played a major role in determining how dramatically the sky might have changed. If the ancient particle storm was accompanied by a large coronal mass ejection directed straight toward Earth, the magnetic environment surrounding the planet may have been strongly disturbed. But the arrival of a plasma cloud alone is not enough to produce a major geomagnetic storm. The direction of the magnetic field within it is also crucial. When that field is favorably oriented to connect with Earth's magnetic field, energy from the solar wind can enter the magnetosphere more efficiently, causing auroras to become brighter and extend much farther than usual. Auroras form when charged particles are guided by magnetic fields into the atmosphere near the polar regions. There, they collide with oxygen and nitrogen, causing atoms and molecules to emit light. The colors can vary according to altitude and the type of gas involved, ranging from green and red to fainter shades of purple. Under ordinary conditions, auroras remain concentrated mainly at high latitudes. But during a powerful geomagnetic storm, the auroral region can expand much farther toward the equator. Places that rarely see auroras may experience bands of light, glowing curtains, or broad red regions stretching across the sky. If the event around 12,350 BCE was accompanied by a sufficiently intense geomagnetic storm, people living at lower latitudes than usual may therefore have witnessed a very unfamiliar sky. The light may have persisted for hours, changing shape and drifting slowly along invisible magnetic field lines high above the atmosphere. However, this remains a reasonable possibility, not a confirmed scene. Tree rings do not preserve the colors of an aurora. Ice cores do not reveal the latitudes at which the light appeared. They show that the atmosphere received an enormous particle flow, but they do not preserve the full structure of the plasma cloud or the orientation of the magnetic field that traveled with it. This distinction is important. An extremely powerful energetic particle event and an extremely powerful geomagnetic storm can occur together, but their strengths are not always directly proportional. The proton flow that produces carbon-14 reflects one part of solar activity, while auroras and magnetic disturbances depend heavily on the characteristics of the coronal mass ejection. For this reason, we cannot claim that the entire sky over Earth turned red. Some regions may have seen auroras, while others noticed nothing unusual. Even during a severe geomagnetic storm, the appearance of the sky would still have depended on location, weather, cloud cover, and the time of day. Nor is there any basis for saying that the ground was scorched. High-energy protons collide mainly with the atmosphere at great altitudes. The atmosphere absorbs and disperses most of their energy before it reaches the surface. The event may have made the radiation environment in space dangerous, but it would not have resembled a vast wave of heat sweeping across forests, mountains, and human beings. The ancient pine trunks do not carry widespread burn marks from the sky. Their carbon-14 spike is a chemical trace, not an injury caused by heat. If a forest fire occurred at the same time, it would need to be demonstrated through charcoal, sediment, or other local evidence. It cannot be inferred solely from the elevated carbon-14 level. The event also cannot be treated as the direct cause of the melting of major ice sheets. The retreat of glacial ice unfolded under the influence of many long-term factors, including changes in Earth's orbit, greenhouse gas concentrations, ocean circulation, and other climate feedbacks. Even a very powerful solar particle storm would have been far too brief to explain such large-scale changes on its own. Similarly, there is no evidence that the event caused a mass extinction. Life on the surface was protected by the atmosphere and magnetic field, and the biological record shows no widespread collapse coinciding with the carbon-14 signal. For humans and animals living at ground level, the direct effects may have been far smaller than the danger such an event would pose to satellites or astronauts in the modern world. Some chemical reactions in the atmosphere may have changed temporarily as the energetic particle flow increased. Ionization levels may have risen, and certain molecules in the upper atmosphere may have been affected. But moving from that possibility to the claim that the event altered the global climate would be a step too far. Short-term atmospheric effects, if they occurred, would not necessarily produce a lasting climatic transformation. There is also no scientific basis for claiming that ancient people saw a second sun. The flare may have caused the sun to brighten at wavelengths invisible to human eyes, such as X-rays or ultraviolet radiation. But that does not mean that a new glowing sphere appeared beside the sun in the sky. Even an extremely powerful flare would be unlikely to make the visible disk of the sun change dramatically to the naked eye in the way often shown in exaggerated images. A person standing on the ground might have noticed nothing unusual during the day, while modern instruments, had they existed, would have recorded a major disturbance at invisible wavelengths. The easiest possibility to imagine remains an aurora at night, but even that must be kept within careful limits. The sky may have displayed red or green regions far from the poles. It is also possible that the accompanying plasma cloud carried a magnetic field with an unfavorable orientation, producing a geomagnetic storm much weaker than the scale of the proton event might suggest. This uncertainty does not make the story less compelling. On the contrary, it shows that every natural archive preserves only one part of an event. Tree rings tell us about carbon-14 entering the biosphere. Ice cores record isotopes that settled with the snow. But the colors of the sky, the shapes of the auroras, and the reactions of the people living at the time all lie beyond the storage capacity of those records. Perhaps a group resting beside a river looked upward and saw an unfamiliar band of light stretching far toward the south. Perhaps they regarded it as an important sign and passed the story to the next generation. But perhaps clouds covered the sky where they lived, or the event did not produce an aurora strong enough at that latitude. Both possibilities remain consistent with what is currently known. Science must therefore stop at the boundary between evidence and imagination. It can confirm that an extraordinarily powerful particle flow struck the atmosphere. It can estimate the event's scale, narrow down its timing, and model the journey of carbon. But it cannot restore a scene that was never preserved in images or written accounts. Sometimes a trace can be extremely precise about one part of the past while keeping the rest hidden. A tree ring can tell us that the atmosphere produced additional carbon-14 during a particular year, but it cannot reveal whether anyone on the ground looked upward. An ice layer can confirm an increase in beryllium-10, but it cannot preserve the red, green, or purple colors of an aurora if one appeared. The sky of early spring in 12,350 BCE therefore remains suspended between knowledge and mystery. We know that a rain of particles arrived. We know that the atmosphere responded. But the scene above the ancient forests and the people who lived among them can only be imagined with caution. That event was not the only one to leave a carbon-14 spike in tree rings. As researchers expanded their measurements to wood from other periods, they realized that the past had preserved several additional events of a similar kind. These rare markers gradually formed a special class of phenomena, recognized by modern science only through the careful reading of tree rings that had survived for centuries. Across hundreds of years preserved in tree rings, most changes in carbon-14 occur gradually. Its proportion may rise or fall with solar activity, Earth's magnetic field, and the way carbon moves through the atmosphere. But these shifts usually do not create a sharp boundary between one year and the next. Occasionally, that familiar rhythm is broken. Carbon-14 increases so quickly that one growth ring becomes clearly different from those beside it. The change does not appear as a colored mark or a crack visible to the naked eye. It emerges only when the wood is measured in a laboratory, yet it is distinct enough to show that the atmosphere once received a much larger than normal flow of energetic particles over a very short period. Today, rare traces like these are commonly known as Miyake events. The name comes from Fusa Miyake, a Japanese researcher who helped open an entirely new way of looking into the history of solar activity. The story began with ancient Japanese cedar trees. Each of their growth rings had been assigned to a specific year, creating a clearly defined timeline. When Fusa Miyake and her colleagues measured the carbon-14 content of individual rings, they found that most years showed only small variations. But at the boundary between the years 774 and 775, the signal suddenly rose dramatically. This was not a change unfolding across many generations of trees. It appeared rapidly, almost entirely within a single year, before gradually blending back into the familiar rhythm of the carbon cycle. That shape led researchers to conclude that the cause was unlikely to have been an ordinary change in forests, climate, or the oceans. At first, no one could say with certainty what had created the signal. Earth's atmosphere may have received a powerful stream of particles from the sun. It was also possible that the energy came from a more distant phenomenon in space. A tree ring could reveal that carbon-14 had increased, but by itself, it could not identify where the event began. Scientists therefore continued searching through other trees. If the carbon-14 spike appeared in only one cedar, it might have been an anomaly unique to that sample. But if trees growing at the same time in many parts of the world preserved a similar signal, the cause would have to be far more widespread. Gradually, the trace from the year 775 was identified in tree ring chronologies from several different regions. Distant ice layers also preserved isotopes produced when energetic particles entered the atmosphere. Independent lines of evidence began pointing toward a global event, most likely caused by an exceptionally powerful solar energetic particle storm. That discovery changed the way humanity studies space weather in the past. Before then, the detailed observational history of the sun extended across only a relatively short interval. Telescopes had existed for a few centuries, while satellites had directly measured the space environment for only a few decades. Compared with the age of the sun, this was only the smallest moment. Tree rings could extend that view much farther into the past. A tree does not observe the sun like a telescope, but it absorbs carbon from the atmosphere during every growing season. When the atmosphere changes, part of that change enters the new wood and becomes preserved. Ancient trees therefore become silent records of events that occurred long before humanity possessed measuring instruments. Not long after the first discovery, another carbon-14 spike was identified around the years 993, 994. It was not identical to the event of 775 and was also smaller, but it still rose far more rapidly than ordinary variations. The appearance of this second signal showed that the spike in 775 was not completely unique. From that point onward, the term Miyake event gradually came to describe rapid increases in carbon-14 preserved in tree rings, often accompanied by corresponding evidence from similar isotopes in ice. The name does not fully describe what occurred on the sun. It refers mainly to the trace the event left within Earth's natural archives. After the two cases from historically documented periods, the search expanded deeper into the past. Researchers measured ancient wood from many regions and many eras. Over time, additional spikes were found in prehistoric periods, when humans had left no written records that could be compared with unusual events in the sky. Every new discovery required careful verification. A growth ring might be extremely thin, missing, or difficult to distinguish from the one beside it. A wood sample might also have been altered during preservation. Scientists, therefore, usually search for the same signal in several trees and compare it with ice cores or other natural archives. When multiple independent traces appear during the same period, the case for an extraterrestrial event becomes more convincing. Most of the well-studied events identified so far are believed to have originated from extremely powerful streams of solar energetic particles. Those particles entered the atmosphere, increased carbon-14 production, and left corresponding signals in trees across many parts of the planet. However, Miyake events do not occur according to a regular rhythm. Two signals are separated by only a little more than 2 centuries, while other cases lie thousands of years apart. The current record is still too limited and contains too many gaps to claim that the sun produces such events at fixed intervals. Not every era left behind enough preserved trees. Many trunks decayed long ago, while surviving samples may still lie beneath riverbeds, inside bogs, or under sediment layers that have not yet been discovered. Some tree ring chronologies have also not been measured year by year, so brief spikes may still remain hidden within the data. The known events, therefore, do not form a calendar that can be used to predict the next one. They show only that the sun has repeatedly produced particle streams far more powerful than the events directly observed during the satellite era. Among these rare traces, the event around 12,350 BCE remains especially prominent. It is older than the other confirmed cases and belongs to an Earth that was still emerging from the Ice Age. The pine trees that preserved the signal grew before the relatively stable climatic period of the modern world had begun. This makes the event remarkable not only because of its age, but also because of the environment through which its signal traveled. The atmosphere contained less carbon dioxide, more water remained locked within ice sheets, and the carbon cycle was not identical to the one operating today. The large spike in the tree rings must therefore be interpreted within the conditions of its own period before it can be used to estimate the strength of the particle event. After these differences were incorporated into models, the ancient event was still regarded as the strongest example identified in the existing record. But the word strongest must be understood calmly. It does not mean the storm was certainly twice as powerful, or many times more powerful, than every other known event. It means only that current measurements and models place it at the highest level among the traces discovered so far. Even more powerful events may still exist without yet having been revealed by trees. New samples may be discovered, and future models may revise the estimated scale of individual events. The history of solar activity still contains many dark gaps, because most of the sun's lifetime passed without human observers. Even so, Miyake events have opened an extraordinarily wide door. They show that tree rings preserve more than the age of a forest, or changes in rainfall and temperature. During a few rare years, they also retain traces of events that occurred about 150 million kilometers from Earth. A cedar tree in Japan, an ancient tree in Europe, and a layer of ice in Greenland can all carry the memory of a particle stream that passed across the entire planet. Objects that never encountered one another become parts of the same record, assembled thousands of years later. The event around 12,350 BCE currently stands at the beginning of that record. But to understand how powerful it truly was, calling it the largest storm is not enough. We must look more closely at the quantities tree rings actually preserve, because the height of a carbon-14 spike and the strength of the solar particle flow do not always change in the same proportion. When the carbon-14 spike from 12,350 BCE is placed beside the signal from the year 775, the difference appears striking. The ancient spike is nearly twice as high, so the first impression is that the storm that produced it must also have been nearly twice as powerful. But tree rings do not directly measure the strength of the sun. They preserve only the remaining signal after particles passed through the atmosphere, produced carbon-14, and were then distributed among the air, oceans, and living world. A taller spike, therefore, cannot be read as a simple number. It is more like the shadow of an object than the object itself. The shape of a shadow also depends on the angle of the light, the distance, and the surface upon which it falls. In the same way, the amount of carbon-14 preserved in a tree ring depends not only on the particle flow from the sun, but also on the conditions on Earth when the event occurred. The first thing scientists observe is the height of the carbon-14 spike. This is the increase measured in one or several growth rings compared with the surrounding years. It shows that the amount of radioactive carbon absorbed by the tree changed sharply, but it does not fully reveal how much carbon-14 was actually produced throughout the entire atmosphere. Some of the new carbon may have remained in the air. Some may have quickly entered the oceans or soil. Another portion was absorbed by trees during the growing season. The amount of carbon-14 found in a trunk is therefore only one part of the total amount that appeared across the planet. Using the tree ring data, researchers must work backward to estimate the total amount of carbon-14 that was produced. Only then can they infer the number of high-energy protons required to create that quantity of the isotope. Every step depends on models, and every model carries a certain range of uncertainty. This makes comparing two events somewhat like tracing a sequence of footprints backward. The tree ring is the final trace. Before it came atmospheric carbon, before the carbon came nuclear reactions, and before those reactions came the proton stream from the sun. The farther researchers move back toward the source, the more the result depends on assumptions about the path the particles followed. The number of protons is not the only important factor. Their energy also makes a major difference. A stream containing an enormous number of particles, most of them at relatively low energies, will not affect the atmosphere in the same way as a smaller stream containing a greater proportion of high-energy particles. More energetic protons can penetrate deeper and create different collision cascades from slower particles. This distribution of energy is commonly called the energy spectrum. Put simply, it describes how the total number of particles is divided between slower and faster groups. Two events may deliver similar numbers of protons to Earth, but if one contains more high-energy protons, the amount of carbon-14 produced can still be significantly different. Tree rings do not preserve the full energy spectrum. They record the final outcome after many types of particles have interacted with the atmosphere. When modeling an ancient event, scientists therefore often choose a well-measured modern event as a reference for how the particle energies were distributed. If the true energy spectrum of the ancient storm closely resembled the modern reference event, the estimate may be reasonably accurate. But if the ancient particles had a harder spectrum, meaning a larger proportion reached high energies, or a softer one, the result could change. This is one reason estimates of the event's scale should not be treated as completely fixed values. After the climate near the end of the Ice Age, Earth's magnetic field and the carbon cycle were included in the model. The event of 12,350 BCE still emerged as the strongest case in the existing record. However, it was not twice as strong as the event of 775, as the difference between the two spike heights might suggest. Estimates from a 2025 model indicate that the particle flow during the ancient event may have been about 18% greater than during the event of 775. That figure comes with a relatively broad range of uncertainty because no one can know the exact energy spectrum, duration, or structure of an eruption that occurred more than 14,000 years ago. 18% may not sound especially large, particularly when the two tree ring spikes look so different. But the event of 775 was itself extraordinarily powerful. Exceeding it, even by a fraction, still places the ancient event far beyond the particle storms directly observed during the satellite era. When compared with the most powerful energetic particle event recorded by modern instruments and used as the reference case in the model, the ancient event may have been hundreds of times larger. Yet this is not a perfectly direct comparison either. It depends on the assumption that the distribution of energy among the protons had a similar shape in both events. If that assumption changes, the estimate of hundreds of times larger may change as well. The greatest value of the comparison, therefore, does not lie in fixing an absolute ratio, but in showing that the ancient event extended far beyond the range directly experienced during the satellite age. This also explains why the event of 12,350 BCE should not be compared with the Carrington event, as though both were measured on the same scale. The Carrington event occurred in 1859 and is famous for producing an exceptionally powerful geomagnetic storm. Auroras appeared in places where they were rarely seen, and telegraph systems were disrupted across many regions. What remains from the Carrington event mainly tells the story of disturbances in Earth's magnetic field and their effects on the technology of the time. The evidence for the ancient event, by contrast, lies primarily in carbon-14 and beryllium-10, showing that the atmosphere received an enormous flow of energetic particles. An event can be extremely powerful in terms of particles without necessarily producing an equally powerful geomagnetic storm. Conversely, an eruption carrying a favorably oriented magnetic field can create a severe geomagnetic storm without producing an exceptionally high carbon-14 spike. The two phenomena may occur together, but they do not always rise and fall in the same proportion. It is therefore impossible to say, with one number, how many times stronger the storm of 12,350 BCE was than the Carrington event. The two are known through different kinds of evidence. Carrington was observed through auroras, telegraph disturbances, and magnetic measurements. The ancient event was recognized through nuclear reactions in the atmosphere and isotopes preserved in trees and ice. What is most certain is that the ancient particle flow was immense. It was powerful enough to produce a clear global increase in carbon-14 and leave a trace that could still be recognized more than 14,000 years later. But the brightness of the flare, the size of the plasma cloud, and the strength of the accompanying geomagnetic storm cannot yet be fully reconstructed. The word strongest must therefore be kept within its proper limits. This is the strongest solar energetic particle event identified so far in the existing isotope record, based on the measurements and models currently in use. It does not mean that every part of the eruption was the strongest, nor does it mean that the sky, Earth's magnetic field, or effects at ground level were certainly greater than those of every other event that has ever occurred. That caution does not make the event seem smaller. On the contrary, it helps reveal what is most remarkable. Even after exaggerated interpretations based on the height of the carbon-14 spike are removed, the event still lies beyond anything modern technology has directly witnessed. In the world near the end of the Ice Age, such a particle storm may have passed without leaving obvious consequences in human life. There were no satellites to malfunction, no astronauts in space, and no electrical grids stretching across continents. The atmosphere absorbed most of the energy, while the final traces remained quietly preserved in trees and ice. But if the same particle flow appeared today, it would enter a completely different world. Thousands of satellites now operate above the atmosphere. Aircraft cross polar regions, human spacecraft travel beyond the protection of Earth's dense air, and power grids and navigation systems have become nearly indispensable parts of modern life. The difference between a carbon-14 spike, a proton stream, and a geomagnetic storm is therefore more than a technical detail in the calculations. It determines the type of danger humanity must prepare for. A powerful particle storm threatens satellites and astronauts differently from a plasma cloud capable of creating a major geomagnetic storm. If both occur together, the effects could spread across several layers of technology at once. The ancient storm cannot be reduced to a single number. But what the tree rings preserved is enough to open a question more important than any comparison. If the sun were once again to release a similar stream of particles, what would a world of satellites, communications, and electrical grids have to face? When people hear about a proton stream far more powerful than anything directly recorded during the satellite era, it is easy to imagine radiation immediately pouring down to the ground and threatening every living thing. But between space and the planet's surface lie two enormous layers of protection: Earth's magnetic field and its atmosphere. Because of them, people standing on the ground are not directly exposed to the full particle storm passing through the space above. Earth's magnetic field is the first protective layer the protons encounter. It extends far beyond the planet, creating a region known as the magnetosphere. Because protons carry an electric charge, their paths can be bent as they enter this magnetic environment. Most particles in the solar wind are deflected away from Earth, while some are guided along magnetic field lines toward regions near the poles. The magnetosphere is not a solid shield, and it cannot stop every particle. Extremely energetic protons can still penetrate farther, especially during major radiation storms. But before reaching the places where people live, they must pass through another protective layer that is far thicker, the atmosphere. From the ground, the air above us may seem light and almost insignificant. Yet the entire column of atmosphere extending upward for many tens of kilometers contains an enormous amount of matter. When a high-energy proton enters the atmosphere, it usually collides with nitrogen or oxygen in the upper layers instead of continuing straight toward the surface. The first collision may produce many smaller particles. These particles continue downward and strike other atoms, creating a cascade of reactions through the atmosphere. Some of these reactions produce carbon-14 and other isotopes that can later be preserved in tree rings. The remaining energy is gradually dispersed and absorbed before reaching the ground. An extreme solar particle event should therefore not be imagined as a wave of radiation that instantly sweeps away life. The people who lived more than 14,000 years ago had no radiation shelters, but the planet itself still protected them. Trees animals, and humans at the surface most likely did not face a global biological catastrophe simply because the proton stream passed overhead. This is also consistent with the surviving evidence. The ancient event produced an enormous carbon-14 spike, but it was not accompanied by signs of a widespread extinction. There is no evidence that forests everywhere were destroyed or that life on land collapsed at the same time. The strongest signal was found not within layers of devastation, but within the chemical composition of wood and ice. However, significant protection does not mean that every location around Earth is equally safe. Shielding becomes less effective as people move to higher altitudes. At the height of commercial aircraft, passengers already have far less air above them than people standing on the ground. Radiation from secondary particles can therefore be higher, especially on routes passing close to the polar regions. The polar regions are more sensitive because the structure of Earth's magnetic field allows some particles to enter the atmosphere there more easily. During a major radiation storm, airlines may need to consider rerouting flights, reducing altitude, or avoiding certain polar routes. This does not mean passengers would certainly face immediate danger, but exposure levels could rise in an environment that already receives more radiation than the surface. The precise level of risk also depends on the types of particles arriving and the energies they carry. A storm lasting many hours and containing large numbers of high-energy protons would differ from a shorter event or one dominated by lower-energy particles. The same storm would not create identical effects at every altitude or latitude. Beyond the atmosphere, the loss of protection becomes much more obvious. Astronauts in low Earth orbit still receive some shielding from Earth's magnetic field and from the structure of their spacecraft. But they do not have a thick layer of air above them like people on the ground. When a powerful particle storm arrives, the radiation environment around them can change rapidly. Spacecraft can be designed with better shielded areas where astronauts can temporarily shelter while radiation levels are elevated. Water, food supplies, and materials rich in hydrogen may be arranged around these areas to help absorb some of the proton's energy. But space and mass aboard a spacecraft are always limited, so the shielding can never be as thick as the atmosphere of an entire planet. Farther beyond low Earth orbit, the risk continues to increase. A spacecraft traveling toward the Moon or Mars may move outside the strongest protection of the magnetosphere. The crew must then depend mainly on the spacecraft's materials, warning systems, and their ability to reach shelter before the most intense particle stream arrives. On the surface of the Moon, the difference is even greater. The Moon has almost no substantial atmosphere and lacks a strong global magnetic field like Earth's. A person standing outside a lunar base would not be protected by kilometers of air. High-energy protons could reach the surface with far fewer obstacles, making an event like the one in 12,350 BCE a much more serious threat. Plans for long-term habitation on the Moon therefore usually include shelters covered by lunar soil, water, or other suitable protective materials. Humans may be able to live and work beyond Earth, but they must recreate part of the function that the atmosphere quietly performs for us every day. Uncrewed spacecraft are also affected. Powerful protons can pass through electronic components, flip a data bit, force a computer to restart, or create errors in sensors. A single particle is extremely small, but if it passes through the right sensitive location, it can cause a change large enough to make a device malfunction. During a major storm, the number of such interactions rises considerably. Satellites may enter safe mode, suspend certain operations, or turn sensitive components toward directions where they are less exposed. These measures cannot guarantee that every device will remain protected, but they can reduce the chance that a small error develops into serious damage. The danger posed by an event resembling the ancient storm still cannot be calculated precisely from tree rings alone. Carbon-14 shows that the energetic particle flow was large enough to change the atmosphere, but it does not preserve the full distribution of energy among the protons. If the event contained many extremely energetic particles, they could penetrate more deeply and be harder to shield against. If most particles had lower energies, the effects might have been concentrated more heavily within the space environment near Earth. The duration of the event also matters. A particle flow that reaches an extremely high peak but ends quickly may produce a different total exposure than a weaker storm lasting several days. A person's location at the time would determine almost the entire level of risk. Standing beneath the atmosphere, flying along a polar route, living inside a space station, or working on the lunar surface are entirely different situations. This is why the question of safety cannot be answered with a simple yes or no. For most people on the ground, the atmosphere and magnetic field provide enormous protection. An extreme event does not mean radiation would instantly become a catastrophe for the entire population. But for people and equipment located higher up, outside these protective layers, or near their edges, the same particle storm could become a serious emergency. What is remarkable is that the very process protecting Earth also created the evidence discovered thousands of years later. The atmosphere did more than slow down and absorb the protons' energy. In the process, it transformed part of their impact into carbon-14. The newly created carbon mixed into the air was absorbed by trees and became preserved within individual growth rings. Without an atmosphere, trees could not exist to preserve the signal. If the atmosphere were not thick enough, the effects of the particle stream at the surface could have been entirely different. The layer of air surrounding Earth is both a shield and the place where an invisible rain of protons is transformed into a chemical trace capable of surviving for many millennia. People on the ground are therefore not entirely defenseless against the sun. We live at the bottom of an ocean of air, beneath a protective layer that most of the time goes completely unnoticed. But above that ocean, thousands of satellites continue moving through an environment much closer to the paths traveled by energetic particles. Those machines would be among the first systems forced to confront another storm of similar magnitude. They are not protected by the full atmosphere, yet they play essential roles in communications, navigation, weather forecasting, and many other quiet processes that keep the modern world functioning. Above the atmosphere protecting humanity, thousands of satellites continue moving silently around Earth. They travel through a region of space that is almost invisible to the naked eye, yet they support many familiar activities on the ground. A phone call crossing an ocean, a navigation map, an image of a developing storm, or the precise time used to synchronize countless systems may all depend on machines flying high overhead. Under ordinary conditions, satellites already operate in an environment that is far from peaceful. They are continually exposed to radiation from the sun and more distant regions of space, experience dramatic temperature changes as they move between sunlight and darkness, and encounter charged particles surrounding Earth. For this reason, many satellites are designed to withstand a certain level of radiation. But an extreme energetic particle event could push that environment far beyond familiar conditions. When a stream of protons arrives, some particles may pass through the outer shell and reach components located deeper inside the spacecraft. Most do not produce any obvious consequence, but sometimes a single particle passing through exactly the right sensitive location is enough to alter the state of a tiny electrical circuit. Inside computer memory, information is stored through electronic states. A high-energy proton can generate an electric charge as it passes through a material, causing a data bit to switch from one state to another. The error may be minor, changing only a temporary value before software detects and corrects it. But if it occurs within an important control instruction, the satellite may respond in an unintended way. A satellite's computer may restart, a sensor may temporarily lose its signal, or a control system may stop functioning for a short period. In many cases, the spacecraft is programmed to recognize an abnormal condition and automatically enter safe mode. Non-essential operations are then suspended, sensitive components are protected, and the satellite waits for new instructions from the ground. Entering safe mode does not mean that the satellite has been destroyed. It is a form of self-protection, much like a machine temporarily drawing inward when the surrounding environment becomes too harsh. Once the particle flow decreases, engineers can inspect its condition, restore the software, and gradually return the spacecraft to normal operation. A major event, however, would not produce only a few isolated errors. If proton levels remained extremely high for many hours, interactions could occur continuously across multiple components. Error correction systems would have to work harder, sensors might produce noisy data, and older spacecraft or those with thinner shielding could struggle to remain stable. Another effect occurs when electric charge builds up on the surface or inside materials. In space, different parts of a satellite may accumulate unequal amounts of charge. If the difference becomes large enough, a small electrical discharge can occur, similar to a spark of static electricity, but taking place inside a highly sensitive machine. That spark may damage a circuit, interfere with a signal, or force the system to restart. Solar panels must also face the particle flow. They are designed to convert light into electrical energy and usually extend outside the main body of the satellite, where there is little thick shielding. High-energy protons can alter the structure of the semiconductor material within them, gradually reducing their ability to generate power. A single storm would not necessarily cause the solar panels to fail immediately, but it could accelerate their aging, adding the equivalent of years of wear within a short period. The satellite might continue operating, but with less available power, limiting how many instruments could be used at the same time and shortening its expected lifetime. Imaging sensors may also be affected. Cameras used to photograph Earth or observe space can record bright streaks and noisy pixels when energetic particles pass through them. During the most intense part of the proton flow, the resulting images may become difficult to use. Some instruments might need to be temporarily turned off to prevent lasting damage, interrupting observations precisely when the space environment is undergoing its most dramatic changes. Beyond direct radiation, solar activity can also alter the orbits of satellites flying close to Earth. When the Sun releases large amounts of radiation into the upper atmosphere, the extremely thin gases at high altitude can heat up and expand. The atmosphere does not suddenly become as dense as it is near the ground, but even a slight increase in density can create additional drag on objects moving at very high speed. For satellites in low Earth orbit, a small but persistent drag force can cause their orbits to descend faster than expected. The spacecraft must use thrusters to raise their altitude again, consuming fuel that is always limited. If operators cannot accurately determine the new level of drag, the satellite's position may also become more difficult to predict, increasing the complexity of tracking and collision avoidance. Some small satellites have little ability to adjust their orbits. During a period when the upper atmosphere expands strongly, they may lose altitude more quickly, shortening their operating lives or re-entering the atmosphere earlier than planned. This does not mean that every satellite in low Earth orbit would fall at once, but an extreme event could make the management of an entire region of space much more difficult. These effects would not remain confined to space. Every satellite is usually one link within a much larger network. If one link temporarily stops working, the system may switch to another satellite or use a backup method. But if many satellites are affected within a short period, gaps begin to appear on the ground. Communications satellites help transmit signals across enormous distances, especially to regions that are difficult to reach with cables. Some systems contain many satellites that can substitute for one another, so the loss of a single spacecraft may not cause an obvious disruption. But a major storm could force several satellites into safe mode at the same time, reducing capacity and making some connections less stable. Weather satellites observe clouds, temperatures, water vapor, and atmospheric movement. Their data is fed into forecasting models every day. If sensors become noisy or data is missing, forecasters still have many other sources of information, but their ability to track hurricanes, heavy rainfall, and weather systems over the oceans could decline. Earth observation satellites also provide images of wildfires, floods, sea ice, drought, and changes in crops. A brief interruption may not cause serious consequences, but But if many instruments are degraded or remain unavailable for long periods, our view of the planet could become less complete at a time when society has grown accustomed to continuous data. Navigation systems have an even broader influence. Their satellites do more than transmit location information. They carry extremely accurate clocks and send timing signals down to Earth. Phones and navigation devices use these signals to calculate distance, but many other networks also depend on them to keep their operations synchronized. Telecommunication systems need precise timing to organize data traffic. Some power grids use timing signals to compare conditions across widely separated regions. Financial operations also depend on timestamps to record the order of transactions. Each individual error may be very small, but when many systems rely on the same source of time, a prolonged disruption could spread much farther than a map temporarily displaying the wrong location. Maritime and aviation systems also use satellite navigation to track their routes, together with radar, maps, and other backup methods. If the signals weaken, aircraft and ships would not immediately lose all ability to navigate, but reduced accuracy would make coordination more complicated, especially in remote regions where ground-based infrastructure is limited. Even so, we should not imagine that a storm resembling the ancient event would certainly erase every satellite from orbit. Spacecraft are not all built the same way. An important military or scientific satellite may have thicker shielding and use electronic components designed to tolerate radiation. Small, lightweight satellites built at lower cost may be more vulnerable. Orbit also makes a difference. Satellites in low Earth orbit remain within part of Earth's magnetic field but are affected by atmospheric drag when the upper atmosphere expands. Satellites in higher orbits experience less drag but may remain exposed longer to regions containing energetic particles. The event's direction, duration, and the way particles spread through the environment around Earth would all influence which areas suffered the strongest effects. The timing of the storm would matter as well. If forecasting centers received enough warning, operators could turn off sensitive instruments, delay orbital maneuvers, or place satellites into safe mode before the particle flow reached its peak. These measures would not eliminate every risk, but they could reduce the number of errors and prevent some avoidable damage. The actual consequences would therefore be unlikely to appear as one moment when every orbit suddenly went dark. They might begin with scattered failures, one satellite losing contact for several hours, an observing instrument being shut down, a group of low-orbit satellites needing to correct their positions, or a navigation system becoming less accurate in certain regions. If the event were large enough and lasted long enough, those problems could begin to overlap. Some satellites would recover quickly, some would lose part of their remaining lifetime, and a small number might never return to service. The final level of damage would depend on preparation, the design of each spacecraft, and the true characteristics of the particle flow, details that tree rings cannot completely reveal. The ancient pine trunks tell us only that the atmosphere once received an extremely powerful rain of particles. They cannot tell us how many protons a particular modern satellite would encounter, whether its shielding would be sufficient, or how its software would respond. But the trace shows that the environment beyond the atmosphere can become far more severe than anything the satellite industry has directly experienced. Even if most satellites survived, the story would not end there. Their signals still have to travel through part of the atmosphere before reaching the ground. During a major solar storm, that layer of air can become strongly ionized and uneven, altering the path followed by radio waves. The machines in orbit may continue transmitting exactly as designed, but the final stage of the signal's journey toward Earth would no longer pass through a quiet environment. Beneath the satellites, the ionosphere would already be beginning to change. Even if a satellite continues operating normally after a storm, the signal it sends toward the ground may no longer travel along a stable path. Between orbit and Earth's surface lie several layers of atmosphere, including one region that is especially sensitive to solar activity. This region is known as the ionosphere. The ionosphere is not a thin layer with clearly defined boundaries. It extends across part of the upper atmosphere, where ultraviolet light and X-rays from the sun are energetic enough to separate electrons from atoms and molecules in the air. The result is a region filled with charged particles, constantly changing between day and night, across seasons, from one location on Earth to another, and according to the level of solar activity. On ordinary days, these changes can be predicted reasonably well. When sunlight reaches a region, ionization increases. As that area moves into night, some electrons and ions gradually recombine, changing the structure of the ionosphere. Modern communications and navigation systems are designed to operate within this continually shifting environment. But when an extremely powerful stream of energetic particles reaches Earth, the ionosphere can change faster and more dramatically than under familiar conditions. Protons entering the atmosphere, especially near the polar regions, create additional collisions and increase the level of ionization. A region of air already containing charged particles becomes denser and more uneven. To someone standing on the ground, this change is completely invisible. The sky may remain clear, clouds may continue drifting, and daylight may appear no different from usual. But radio waves traveling through the atmosphere encounter a new environment where they may be absorbed, bent, or transmitted at a slightly different speed than expected. High-frequency radio waves are often used for communication across very long distances. Instead of requiring a satellite between two locations, a signal can travel upward toward the ionosphere, bend, and return to the ground hundreds or thousands of kilometers away. This method allows ships, aircraft, and stations in remote regions to remain in contact, even where complete ground-based networks do not exist. During a severe radiation storm, however, increased ionization near the poles can cause more of the radio wave's energy to be absorbed. The signal weakens as it travels, sometimes until it is no longer strong enough for receiving equipment to detect clearly. A connection that was previously stable may become intermittent, fill with static, and then disappear for hours. Flight routes crossing the Arctic and Antarctic are particularly sensitive to this effect. In those regions, communications satellites may appear low near the horizon, while high-frequency radio remains important for maintaining contact with air traffic control. If those signals are absorbed, aircraft may have to move to another route, descend to a lower altitude, or divert toward regions with more reliable communication systems. This does not mean an aircraft would immediately lose control. Flight crews still have multiple instruments and backup procedures, but a prolonged interruption would make coordination more complicated, especially in places where airports are widely separated and ground infrastructure is limited. While proton streams increase ionization near the poles, an accompanying geomagnetic storm can create a different kind of disturbance. When a plasma cloud from the sun interacts strongly with Earth's magnetic field, energy is transferred into the environment surrounding the planet. Electrical currents develop in the upper atmosphere, while electrons within the ionosphere are redistributed in ways that are difficult to predict. In some places, electron density increases, while in others it decreases. Uneven structures may form, drift, and change over short periods. The ionosphere no longer behaves like a relatively smooth layer, but becomes a rippling environment in which the density of charged particles is constantly shifting. Navigation signals from satellites must pass through this region before reaching phones, ships, aircraft, or monitoring stations on the ground. Because radio waves interact with electrons along their path, the signal's travel time may be delayed by a very small amount. Under ordinary conditions, navigation systems can estimate and correct for this delay fairly well. But when the ionosphere changes too rapidly, correction models can no longer keep up completely. The signal still reaches the receiver, but its travel time differs from the expected value. The difference may last for only a tiny fraction of a second, yet satellite navigation depends precisely on measuring intervals this small. A navigation receiver determines its position by comparing the arrival times of signals from several different satellites. Because those signals move at the speed of light, even a very small timing error can become a significant distance error. When several signals pass through unstable regions of the ionosphere at once, the calculated position may fluctuate, become less accurate, or temporarily become impossible to determine. For someone using a phone to navigate through a city, a small error may simply place the location marker on the opposite side of the street. But for systems requiring high precision, the same level of error can matter much more. Aircraft use satellite navigation as one part of their guidance systems. Ships rely on it to maintain their routes and pass through narrow waterways. Surveying teams use satellite signals to determine property boundaries, construction locations, and extremely small movements of the ground. Precision agriculture uses them to guide machinery along nearly parallel paths across fields. In these activities, an error would not necessarily cause an immediate disaster. Specialized systems usually include warnings, verification methods, and alternative sources of information. But if accuracy declined across a wide area for many hours, operations might have to slow down, pause temporarily, or shift into a less automated mode. Some industries require more than position alone. They also depend on extremely precise time. Navigation satellites carry atomic clocks and transmit timing signals down to Earth. Many telecommunications networks use those signals to keep their stations synchronized. Data centers, financial systems, and parts of the electrical infrastructure also depend on accurate timing to arrange events in the correct order. Most users never notice this dependence because timing signals do not appear as a separate service. They operate quietly behind phone calls, transactions, streams of data, and control processes unfolding every second. When the signals become unstable, the effects may appear as small errors that are difficult to connect immediately with a storm occurring far beyond the atmosphere. A telecommunications station may briefly lose synchronization. A measuring instrument may receive an inaccurate timestamp. A trading system may have to switch to a backup clock source. Each individual problem may be manageable, but if many networks are affected at once, maintaining stable operations becomes more difficult. Radio signals from satellites may also fluctuate rapidly in strength and phase as they pass through uneven regions of the ionosphere. The effect is somewhat similar to the way starlight appears to twinkle as it travels through the atmosphere, although in this case, the variation occurs in a radio signal. A receiver may lose its lock on the signal, regain it, and then lose it again within a short period. Near the equator and the polar regions, disturbances like these can be more pronounced because of the ionosphere's natural structure. During a powerful geomagnetic storm, the affected regions may expand and become more difficult to predict. Two receivers separated by a relatively short distance may still experience different signal quality because their transmission paths pass through different parts of the atmosphere. The effects of a storm, therefore, do not appear evenly across the entire world. Radio communications may be disrupted in one region while another continues operating almost normally. A navigation system may lose accuracy for several hours and then recover, while another area remains disturbed longer because of local conditions. The severity of the effects also depends on whether the ancient particle event was accompanied by a major geomagnetic storm. Tree rings show that an extremely powerful stream of energetic particles reached the atmosphere, but they do not preserve the full orientation of the magnetic field inside the accompanying plasma cloud. If that magnetic structure did not connect strongly with Earth's magnetic field, disturbances in the ionosphere may have been more limited. If the connection was favorable, the effects could have been deeper and more widespread. A carbon-14 spike, therefore, cannot be used to claim that every modern signal would certainly stop working. What can be said is that an event of similar magnitude would push the ionosphere into a highly unusual state, making radio transmission and navigation more difficult to predict for a period of time. Modern society has many ways to reduce this risk. Aircraft and ships retain alternative navigation systems. Important networks have backup clocks. Ionospheric monitoring stations continually measure changes in electron density and update correction models. When space weather warnings are issued, some operations can be adjusted before the strongest disturbances arrive. Yet our dependence on signals from space remains profound. In only a few decades, Satellites have become part of our infrastructure, even though they orbit far beyond the cities and cables people are accustomed to seeing. Space is no longer simply a place for scientific observation. It has become part of Earth's communications, transportation, surveying, and timekeeping systems. A solar storm, therefore, does not need to destroy satellites to create disruption. Simply by altering the layer of atmosphere through which their signals must travel, it can cause distances to be calculated incorrectly, weaken communications, and reduce the accuracy of timing systems. Extremely small disturbances high above Earth can spread into countless activities below. Beneath those invisible transmission paths lies another network that is even more extensive. Electrical lines stretch across cities, plains, and national borders, connecting thousands of power plants and substations into shared systems. If Earth's magnetic field begins changing rapidly, the very length of this network can cause it to collect electrical currents that were never produced by any power station. Radio signals may be distorted when the ionosphere changes, but closer to the ground there is another system that is also highly sensitive to solar activity. It is the electrical grid stretching across cities, plains, and vast regions of land, connecting power plants with substations, industrial areas, and millions of homes. The power grid is built to carry electricity generated by humans. During a powerful geomagnetic storm, however, long transmission lines can also pick up another kind of current, one that does not come from any power plant. It is produced when the magnetic field surrounding Earth changes rapidly enough. This must be clearly distinguished from the energetic particle event recorded in tree rings. A powerful proton stream can increase carbon-14 production in the atmosphere, but it does not directly create large currents in electrical networks on the ground. The main danger to the power grid arises when a cloud of plasma and magnetic field from the sun reaches Earth and produces a severe geomagnetic storm. A coronal mass ejection can carry an enormous volume of material together with an embedded magnetic field. As this structure approaches Earth, the direction of its magnetic field becomes extremely important. If it is favorably oriented to connect with the planet's magnetic field, energy can enter the magnetosphere more efficiently, causing Earth's magnetic field to fluctuate strongly for many hours. These changes do not occur equally everywhere. They are often more pronounced in regions closer to the poles, but during a sufficiently powerful storm, the effects can extend toward lower latitudes. A changing magnetic field in the space above Earth also creates very weak electric fields across the planet's surface. Those electric fields are far too small for people to feel directly. Someone standing outdoors would not see sparks or feel electricity passing through the body. But when an electric field acts across a conductor extending for hundreds or thousands of kilometers, the small effect along each section can add together and produce a significant voltage. Transmission lines are conductors of this kind. They connect distant regions, pass across many types of soil and rock, and link to grounding systems at substations. During a geomagnetic storm, induced currents can travel through the ground, enter the electrical network at one location, and leave it at another. This current differs from the alternating current normally carried by the grid. It changes much more slowly, and can be treated as an almost direct current entering equipment that was never designed to receive it. The components most vulnerable to this effect are the large transformers located at critical points in the network. Transformers raise or lower voltage so electricity can be transmitted over long distances and then distributed safely to users. Inside them are coils of wire and metal cores designed to operate within a particular magnetic range. When induced current enters, the magnetic state of the core can be pushed away from normal operating conditions. If the effect is mild, the transformer may continue operating while producing additional noise, vibration, or heat. If the current becomes strong enough and persists, the equipment may heat more rapidly, consume additional reactive power, and make voltage across the grid more difficult to keep stable. Operators may see disturbances appearing at several substations almost simultaneously. Voltage begins to fluctuate, protective systems issue warnings, and some transmission lines start operating outside their normal range. Under those conditions, operators may need to reduce load, change how electricity is distributed, or separate part of the grid to prevent the disturbance from spreading. Disconnecting a region does not necessarily mean the system has lost control. Sometimes it is a deliberate measure used to protect critical equipment. Certain areas may temporarily lose power, but isolating them can help the rest of the network remain operational and reduce the risk of long-term damage. The difficulty is that the electrical grid is not a collection of isolated devices. It is one vast interconnected system in which a change in one place can affect many others. If one transmission line is disconnected, electricity shifts onto the remaining routes. Those lines must then carry additional load, and if they are also being affected by the geomagnetic storm, stress throughout the system can increase. In a worst-case situation, the imbalance could spread across a wide area. An overheating transformer might have to be taken offline. Another transmission line would receive additional load, voltage would fall, and protective systems would continue disconnecting more equipment. This is how a relatively small initial disturbance could develop into a large-scale power outage. A geomagnetic storm, however, would not inevitably lead to such an outcome. The severity of its effects would depend on many factors: the strength and rate of change of the magnetic field, geographic location, the structure of the rock and soil below, the length of transmission lines, transformer design, and the way grid operators respond. Rock and soil do not conduct electricity in the same way everywhere. In some regions, induced currents can pass through the ground relatively easily, while in others, the surface electric field becomes stronger. Two electrical networks at the same latitude may therefore experience very different levels of disturbance. Extremely long transmission lines are often more sensitive because induced voltage can accumulate across great distances. Networks at high latitudes also tend to receive greater attention because they lie closer to regions of intense geomagnetic activity. But during a sufficiently powerful event, the effects would not necessarily remain confined to the polar regions. Other long conductors besides power lines can also collect induced currents. Metal pipelines extending across large regions may experience small changes in electrical potential that affect their corrosion protection systems. Communications cables containing metal or extensive grounding networks may also record disturbances. Modern fiber optic cables transmit data through light, so the glass fibers themselves do not directly conduct electricity like traditional metal cables. However, long cable routes may still include repeaters, power supply equipment, and grounding systems. The infrastructure as a whole must therefore still be considered in plans for responding to space weather. One famous example of technology's vulnerability to geomagnetic storms is the Carrington event of 1859. At the time, telegraph systems were among the first electrical communications networks extending across large regions. During the storm, unusual currents appeared in some lines, equipment produced sparks, and operators struggled to control the system. In some places, telegraph equipment continued operating for a time even after its main power source had been disconnected, because the induced current in the wires was strong enough to transmit signals. This demonstrated that a changing magnetic field can introduce energy directly into long conductors on the ground. But the Carrington event was not a duplicate of the event in 12,350 BCE. The two events are known through different kinds of evidence. Carrington was recorded through observations of the sun, auroras, magnetic disturbances, and effects on telegraph systems. The ancient event was identified mainly through carbon-14 in tree rings and related isotopes preserved in ice. From the carbon-14 spike, scientists can conclude that an enormous stream of energetic particles entered the atmosphere. But they cannot determine with certainty whether an accompanying coronal mass ejection was directed toward Earth, how its internal magnetic field was arranged, or how strongly the magnetic field at the surface changed. An event may produce an enormous number of protons, while creating only a moderate geomagnetic storm. Conversely, an eruption with a less remarkable particle flow may still cause a powerful geomagnetic storm if its magnetic structure connects efficiently with Earth's magnetic field. The carbon-14 increase, therefore, cannot be translated directly into an expected scale of power outages. What can be said is that if a similar particle event were accompanied by an extremely powerful coronal mass ejection carrying a magnetic orientation unfavorable to Earth, the modern electrical grid would face a serious situation. Induced currents could appear across wide regions, many transformers could come under stress at the same time, and operators would have to make decisions while geomagnetic conditions continued to change. Some large components cannot be replaced quickly. High-power transformers may be custom-built, difficult to transport, and require considerable time to install. If several such units were damaged at once, restoring the grid would be far more complicated than recovering from an ordinary weather-related outage or technical failure. Even so, we should not imagine that a storm would certainly burn out every transformer in the world. Electrical networks differ between countries in their structure, standards, and level of preparation. Many systems already use sensors to monitor induced currents, forecasting models, and operating procedures designed specifically for geomagnetic storms. When a warning is received, operators may reduce power flow along sensitive routes, postpone maintenance, place additional backup generation on standby, or change the way the network is connected. They may also monitor transformer temperatures and unusual currents so they can intervene before equipment exceeds safe limits. The storm would not necessarily produce its strongest effects at the moment the flare's light reached Earth. The plasma cloud usually requires additional time to cross space. This delay can provide an opportunity to prepare, although not every dangerous feature can be known far in advance. The orientation of the magnetic field inside the ejected cloud is particularly difficult to determine accurately while it is still far away. Only when the cloud approaches monitoring spacecraft positioned between the Sun and Earth can instruments directly measure the magnetic structure that is coming. By then, the final warning time may be relatively short. Forecasting, therefore, still has limits. Humanity can observe an eruption and estimate its speed and direction, but may not fully understand how it will interact with Earth until the event is already quite close. Even so, this limitation does not mean society can do nothing but wait. Every monitoring station, observing satellite, and forecasting model adds to the available preparation time. Every transformer that is better monitored, every backup system, and every operating procedure that has been practiced reduces the chance that a disturbance in space will become a prolonged crisis on the ground. Induced currents within the grid cannot be prevented entirely because they arise from changes in the magnetic field on a planetary scale, but their consequences depend greatly on how human systems are designed and operated. A network that understands its vulnerabilities has far more opportunity to adapt than one that begins responding only after equipment starts to fail. The ancient storm passed through a world without power lines, transformers, or extensive grounding networks. It left traces only in the atmosphere, trees, and ice. If a similar event returns, its interaction with Earth will take place not only within nature, but also within the networks humanity has constructed across the planet's surface. Our ability to predict such an event is still imperfect, but humanity is no longer completely blind to the sun. Observatories are watching active regions, satellites are measuring radiation and the solar wind, and many systems on the ground are prepared to change their operating state when warnings appear. The next question, then, is not only what the storm could do, but how much we may be able to accomplish before it arrives. An extreme solar storm may begin about 150 million kilometers from Earth, but today, humanity no longer learns of it only after the effects have already appeared. Many instruments continuously monitor the Sun, the environment between the planets, and the region of space surrounding Earth. Each layer of observation follows the next, from the moment energy begins accumulating on the star to the point when a plasma cloud approaches our planet. Forecasting remains limited, but every signal received can extend the available preparation time. Sometimes that window lasts only a few minutes. In other cases, humanity may have many hours, or more than a day, to place important systems into safer operating states. The first layer of observation is focused directly on the Sun. Telescopes on the ground and in space continuously monitor active regions, where powerful magnetic fields appear alongside groups of sunspots. They observe the sun at many different wavelengths, because a region that looks relatively ordinary in visible light may appear much more clearly in ultraviolet light or X-rays. A sequence of images allows scientists to follow the way magnetic structures change. A group of sunspots may expand, the plasma loops above it may become increasingly complex, and energy may continue accumulating for several days. These signs reveal that a region is highly active, but they cannot determine exactly when it will erupt. The sun does not operate like a machine following a fixed schedule. A highly complex magnetic region may remain in place for a considerable time without producing a major eruption. Conversely, a rapid change can sometimes trigger a flare before all the warning signs become completely clear. Monitoring an active region is therefore like watching a system build tension without knowing the exact moment when its structure will rearrange itself. When a flare begins, satellites observing X-rays and ultraviolet radiation can detect it almost immediately. The radiation takes only a little more than 8 minutes to reach Earth, so by the time instruments record the signal, the event's light has already reached the atmosphere. In this situation, the available response time is extremely short. The fastest energetic particles may also arrive relatively early. If the interplanetary magnetic field provides a favorable pathway, protons can travel from the active region to the area near Earth far more quickly than a large plasma cloud. Particle detectors in space monitor the increase in particle flow and rapidly transmit data to forecasting centers. For satellites and astronauts, this stage is especially important. Once proton levels begin to rise, the radiation environment can change quickly. Operators may have only a short time to turn off sensitive sensors, postpone complex procedures, or place a spacecraft into a safer configuration. Astronauts may be instructed to move into a better shielded area. On a space station or spacecraft, this shelter is not necessarily an entirely separate room. It may instead be a location surrounded by materials capable of reducing some of the proton's energy. Water, food supplies, and equipment can be arranged to provide additional shielding around the area. If people are working on the moon or outside a spacecraft, early warning becomes even more important. They need enough time to return to the base, move into a heavily shielded area, or stop activities on the surface. In space, even a few tens of minutes of preparation can make a major difference. Not every part of a solar storm arrives at the same speed, however. A coronal mass ejection usually moves more slowly than light and the first arriving protons. Once it is observed leaving the sun, the plasma cloud may take roughly 1 to several days to reach the region near Earth. This interval provides a broader opportunity for preparation. From images of the eruption, scientists can estimate its direction, speed, and the likelihood that it will pass across Earth. Computer models continue tracking the way the cloud expands through the solar wind and predict when it may arrive. But one important detail remains difficult to determine while the plasma cloud is still far away: the orientation of the magnetic field within it. This orientation strongly influences whether the cloud will interact weakly or powerfully with Earth's magnetic field. A large eruption may reach the planet, but produce only a moderate geomagnetic storm if its magnetic structure is unfavorable for transferring energy. Another cloud may transfer energy much more efficiently and create widespread effects. Only when the plasma cloud approaches monitoring spacecraft positioned between the Sun and Earth can its internal magnetic structure be measured more directly. These spacecraft act like offshore warning stations, standing ahead of Earth along the path traveled by the solar wind. When the plasma cloud reaches one of these monitoring stations, instruments measure its speed, particle density, and magnetic field orientation. The data is transmitted to the ground, helping forecasting centers evaluate the likely severity of the coming geomagnetic storm. However, only a relatively short distance remains between those spacecraft and Earth, so the final warning time may be limited to several tens of minutes or about an hour. That is not enough time to build new infrastructure or replace equipment, but it is still sufficient to carry out steps that have already been prepared. The value of space weather forecasting, therefore, lies not only in knowing that a storm is coming. It also depends on whether each industry already has procedures in place to respond to that warning. Satellite operators can place spacecraft into safe mode. Vulnerable sensors can be switched off, software updates and complex maneuvers can be postponed, and the satellite can be turned into an orientation that offers greater protection to its most important components. Some satellites in low Earth orbit may require changes to their flight plans if the upper atmosphere is expected to expand. Operators monitor altitude, drag, and the positions of nearby objects to reduce the risk of unexpected orbital changes. Maneuvers are not necessarily performed during the most intense part of the storm, because using thrusters in a highly disturbed environment may introduce additional risks. In aviation, warnings about radiation storms and radio disruptions may lead to changes in certain polar routes. Aircraft may be redirected toward lower latitudes, where communications are more stable and radiation levels are lower. This makes flights longer and consumes more fuel, but it reduces risk while the space environment is unusually disturbed. On the ground, electrical grid operators monitor geomagnetic warnings together with data from magnetic observatories. If the risk increases, they may reduce power flow along sensitive transmission routes, change the way the network is connected, or place additional backup generation on standby. Some maintenance activities may be postponed so that more equipment remains available for operation. Important transformers can be monitored closely for rising temperatures and abnormal currents. When necessary, part of the grid may be deliberately separated to limit the possibility of a disturbance spreading. These decisions cannot prevent Earth's magnetic field from changing, nor can they eliminate induced currents in long transmission lines. But they can reduce stress on equipment and prevent a temporary disturbance from developing into lasting damage. Communications and navigation systems also require backup options. Aircraft retain navigation methods beyond satellite signals. Ships have radar, maps, and independent ways to determine their position. Critical networks may use local clocks to maintain accurate timing for a limited period if satellite signals are interrupted. Backup systems may not provide the same accuracy or convenience as the primary services. But while the storm is passing, the most important goal is to preserve essential functions rather than keep every operation running as perfectly as it would under normal conditions. The ability to respond also depends on whether warnings reach the right places. Space weather forecasting centers gather data from many sources and send information to the aviation industry, satellite operators, power utilities, and other relevant organizations. Each sector is concerned with a different part of the event. An airline needs to know about radiation levels and the possibility of communication loss near the poles. A satellite operator is concerned with proton flux and disturbances in orbit. The power industry monitors magnetic field changes that may create induced currents. A general warning about a solar storm is therefore not enough. The information must be translated into specific risks for each system. Even if every observing instrument works properly, forecasts can never be completely precise. The sun is enormous, and its eruptions have complex structures. A plasma cloud may change shape as it travels, interact with other streams of solar wind, or merely brush past the edge of Earth instead of striking the planet directly. Energetic particles also do not spread in the same way during every event. Sometimes the proton stream arrives quickly and powerfully while the main eruption moves in another direction. At other times, a geomagnetic storm becomes significant, even though the initial particle flow was not especially remarkable. Space weather forecasts must therefore be updated continuously as new data becomes available. The practical goal is not to predict every detail with perfect accuracy several days in advance. What matters more is recognizing the possibility of an event early, gradually narrowing the range of uncertainty, and helping important systems shift into appropriate operating states as the level of risk changes. Humanity also cannot build every satellite, transformer, or spacecraft to withstand any storm the sun might possibly produce. Thicker shielding makes satellites heavier and more expensive. Backup equipment makes systems more complicated. Reducing power grid loads too early may disrupt normal operations if the storm ultimately proves weaker than expected. Preparation is always a balance among risk, cost, and certainty. To find that balance, humanity needs to understand the limits the sun has reached in the past. But the satellite era is far too short to provide the entire answer on its own. This is where ancient events become important. The carbon-14 spike in tree rings shows that the sun has produced particle streams far more powerful than anything directly measured by modern instruments. It allows engineers and scientists to consider scenarios extending beyond the narrow range of recent observational history. This does not mean every system must be designed to survive an exact repeat of the event in 12,350 BCE. Tree rings do not fully reveal its energy spectrum, duration, or the strength of any accompanying geomagnetic storm. But they show that the limits worth considering may lie far beyond the events observed during the past several decades. Understanding the past helps humanity ask better questions about the future. How thick should a shelter aboard a spacecraft be? How many errors should a satellite be able to recover from automatically? Which weaknesses should electrical grids monitor? How long can navigation and timing systems continue operating if satellite signals deteriorate? None of these questions allows humanity to control the sun. The star continues to operate according to its own plasma and magnetic fields, independent of what is happening on Earth. But a clearer understanding of the sun's possible range of activity allows society to prepare more suitable protective layers, procedures, and backup plans. Humanity cannot prevent a storm from erupting, but it can reduce the number of satellites performing sensitive operations when the particle flow arrives. It cannot stop Earth's magnetic field from changing, but it can reduce loads on transmission lines that are especially vulnerable. It cannot create a thick atmosphere around the moon, but it can build shelters beneath layers of soil and rock. The ability to adapt lies in decisions like these. It does not create a perfect shield, but it can turn a completely unexpected event into a situation that has already been considered, modeled, and practiced. What is remarkable is that part of this preparation did not begin with the newest satellites or the most powerful computers. It began with trees that died long before modern civilization appeared. Without sensors, wires, or electronic memory, they still preserved evidence of a solar limit that today's instruments have never directly witnessed. From those small rings of wood, humanity has learned what our nearest star may be capable of. And by understanding that ancient past, the systems of the future have a greater chance of remaining resilient when the sun once again enters a more violent moment. For most of history, humanity has observed the sun by looking upward. Telescopes monitor its bright regions, satellites measure its radiation, and instruments in space count the streams of particles passing by. But these tools have existed for only a very small part of the past. Before the age of telescopes and satellites, the sun was still active, still passing through quiet periods, and occasionally releasing enormous particle streams toward Earth. There simply were no instruments waiting to record them. Yet Earth did not remain completely silent in the face of those events. The atmosphere responded, new isotopes were created, carbon entered trees, and snow captured tiny particles from the air. Through these natural processes, the planet unintentionally built a network of archives extending across thousands of years. A tree has no lens, sensor, or antenna. It does not turn toward the sun to monitor individual eruptions. It simply does what it has always done during each growing season: absorb carbon dioxide, use light to create new matter, and add another layer of wood around its trunk. But this very regularity allows a tree to become a very different kind of observatory. Each layer of wood preserves some of the carbon present in the atmosphere when that layer formed. If the amount of carbon-14 changes, the new wood carries that change as well. A particle storm beginning millions of kilometers away can therefore leave a signal inside a living structure on the ground, even though the tree has no awareness of what has happened above it. Because of tree rings, the history of solar activity is no longer limited to the few decades observed by satellites. Ancient wood allows science to look backward through centuries, millennia, and eventually into a world that was still emerging from the Ice Age. The carbon-14 spike around 12,350 BCE is one of the clearest examples. It shows that the Sun once produced a particle stream far beyond anything directly measured by modern instruments. But the value of the signal lies in more than identifying a record-breaking event. It also helps humanity understand more clearly how carbon moves through the atmosphere, oceans, and living world. When carbon-14 is created high in the atmosphere, it does not travel directly into a tree ring. Winds must carry it. It must become part of carbon dioxide, and it must move through many parts of the Earth system. Some enters the oceans, some remains in the soil, and some is absorbed by plants. By comparing the way the signal appears and then gradually declines over several years, scientists can test whether models of the carbon cycle accurately reflect the real world. If a model carries carbon downward too quickly, the simulated spike will appear earlier than the signal preserved in the tree. If the ocean absorbs too much or too little, the shape of the changing signal will also differ. A very brief event on the Sun, therefore, becomes a test of processes operating across the entire planet. Tree rings also help scientists study Earth's magnetic field in the past. The magnetic field deflects some charged particles, so its strength influences how much carbon-14 is produced. When isotope, climate, and geomagnetic data are considered together, they help researchers understand how the invisible protective field surrounding the planet has changed over time. But perhaps the most remarkable role of Miyake events lies in their ability to mark specific years. A rapid carbon-14 spike can appear in trees growing across many regions of Earth. Once the signal has been securely tied to a particular year, it becomes a reference point against which other wood samples can be compared. In archaeology, an ancient piece of wood may still preserve dozens or hundreds of growth rings, yet no one may know exactly which years they represent. The rings remain in their correct sequence, like a section of a calendar with every page intact, but all the dates removed. If a distinctive carbon-14 spike appears within that sequence, it can help place the entire wood sample in its correct position on the calendar. A beam from an ancient structure, a fragment of wood from a ship, or a support post from an old settlement may therefore be dated with much greater precision. A single tree ring carrying a distinctive signal can help connect human events to a specific point in time. Construction timber is not the only material capable of preserving the trace. Any plant that absorbed carbon while the event was unfolding may carry part of the signal. Seeds burned in an ancient hearth, plant fibers used for weaving, pieces of papyrus, or organic materials preserved in dry environments may all contain carbon from the same period. A signal that once passed through the entire atmosphere can therefore remain inside very small objects. A grain of cereal, a strand of cord, or an unremarkable piece of wood may carry the same temporal marker as a large tree growing thousands of kilometers away. This creates an extraordinary connection between astronomy and human history. An eruption on the Sun can help identify the year in which a tree was cut down, a house was built, or an ancient community lived in a particular place. The activity of a star becomes a temporal pin for stories unfolding on the ground. Ancient wood chronologies that have not yet been connected to an absolute calendar can also be joined in a similar way. When the same carbon-14 spike appears in several samples, periods that had previously been floating begin to find their proper position. Separate sequences move closer together, like fragments of a map finally discovering a shared point of reference. Every newly identified spike, however, does more than answer questions about time. It can also change the way humanity understands the Sun. During the few decades of satellite observation, we have witnessed only a very small range of the states our star may experience. Tree rings show that in other eras, the Sun moved far beyond that familiar range. Even so, the historical record still contains many gaps. The events identified so far are only the traces that survived in samples preserved well enough to be studied. Most trees that once lived have long since decayed. Many ancient forests remain buried deep beneath sediment or below land that has not yet been explored. Other carbon-14 spikes may still lie hidden in wood, waiting to be recognized. Even for the event around 12,350 BCE, science has not yet seen the entire story. We know that an enormous particle stream entered the atmosphere, but we cannot reconstruct the exact structure of the eruption that produced it. No one knows what shape the magnetic region on the Sun had, how long the eruption lasted, or whether the particles were accelerated in one stage or several. The way energy was distributed among the protons also cannot be fully recovered. Tree rings preserve the final result in carbon-14, but they do not separately record the faster and slower groups of particles. Models must use modern events as references, even though the ancient storm may have had a different structure. The accompanying coronal mass ejection, if there was one, also left no clear record. It may have been directed toward Earth, traveled off to one side, or merely brushed past the region of space near the planet. The magnetic field inside the plasma cloud may have connected strongly with Earth's magnetic field, or it may not have. The strength of the geomagnetic storm at the time, therefore, remains unknown. Auroras may have extended toward very low latitudes. It is also possible that the proton stream was extremely powerful, while the geomagnetic storm remained only moderate. Carbon-14 alone cannot choose confidently between these possibilities. Science also does not yet know where the ultimate limit of solar activity lies. The strongest event discovered so far may be close to the greatest event the Sun is capable of producing, or it may simply be the largest one preserved in the samples currently available. An older tree or another ice chronology may one day reveal an even greater signal. The frequency of events like these also remains difficult to determine. They do not appear at regular intervals, and the natural record still contains far too many gaps. We cannot look at a few known dates and conclude that a similar storm will certainly return after a specific number of years. This does not mean science knows nothing about the risk. It simply means the risk must be understood as a range of possibilities rather than a precise appointment on the calendar. An event may be extremely rare, but if its potential consequences are large enough, preparation still matters. Every new tree sample that is measured helps make that range of possibilities clearer. A newly discovered spike may add another case to the record. Failing to find a signal across a long chronology is also valuable because it helps place limits on how frequently extreme events may occur. In laboratories, tree rings therefore continue to be separated into thin slices. Very small samples are cleaned, converted into a suitable form, and placed inside measuring instruments. On the screen, most of the data appears as a sequence of gentle variations extending across many years. But among thousands of ordinary values, a single point may sometimes begin to rise. It may be nothing more than an error, a problem with the sample, or a local fluctuation. Researchers will measure it again, search for additional trees, and compare the result with distant ice records. If the signal remains, a previously unknown part of the Sun's history will begin to emerge. This image returns the story to its original stillness. A giant telescope is not always required. Sometimes all that is needed is a slice of wood, a fine needle, and enough patience to read each annual ring. Through these extremely thin layers of wood, trees become observatories that endure longer than any instrument humanity has ever built. They do not observe through light. They observe by living, absorbing the air, and preserving part of the world within their trunks. Every growing season brings another portion of the atmosphere into the wood. And during a few exceptionally rare seasons, the carbon of Earth also carries a trace of the Sun's violence. Scientists continue searching for small spikes among thousands of tree rings because even one new signal could change the limits humanity places on our nearest star. It may confirm that the ancient event remains the most powerful known case. Or another tree may reveal an even more violent moment buried deeper in the past. Whatever the final answer may be, tree rings have already accomplished something remarkable. They connect an event on the Sun with the atmosphere, the climate, the history of life, and the future of technology. It all begins with lines of wood so thin and quiet, preserved inside a tree that fell long ago. Returning to the slice of wood from the beginning of the story, nothing on its surface suggests a storm in space. The tree ring does not glow, carry a burn mark, or resemble the shape of an explosion. To the naked eye, it is only a thin line among many others, formed as the tree passed through one more growing season. Yet inside that layer of wood are atoms that once traveled farther than any movement the tree itself ever made across the ground. The journey began on the sun, where plasma and magnetic fields are always in motion. Within an intensely active region, energy accumulated and was then released. A stream of protons was accelerated, escaped from the star, and began crossing the vast space between the sun and Earth. The fastest particles reached the region near the planet before the larger plasma cloud. They encountered Earth's magnetic field, entered the atmosphere, and collided with nitrogen and oxygen. Through those invisible collisions, more carbon-14 than usual was created. The new carbon did not immediately enter the tree trunk. It combined with oxygen, became part of carbon dioxide, and drifted through the layers of the atmosphere. Winds carried it downward. Some entered the oceans, some traveled toward other regions of the planet, and a small amount eventually reached the leaves of a pine tree preparing to begin its growing season. The tree absorbed that air without knowing it contained the trace of an event that had occurred about 150 million kilometers away. The carbon passed through the leaves, became part of living matter, and remained within the new layer of wood forming around the trunk. The growing season came to an end. That layer stopped expanding and was covered by another ring the following year. The trace from the sun gradually moved deeper into the trunk, resting quietly among countless ordinary carbon atoms. The tree continued to live, perhaps for many more years. It received more sunlight, endured cold seasons, drew water from the ground, and created additional layers of wood. Then one day, the trunk fell. Water may have carried it for a short distance before sediment covered it. In an environment sealed well enough, decomposition slowed, allowing the wood to survive through time. Ice continued to melt, sea levels rose, forests changed, and generations of people appeared and disappeared. The first villages formed, agriculture began, cities were built, and civilizations followed one another. Throughout all these changes, the small growth ring remained motionless beneath the ground. When people finally brought the tree back into the light, no one could see the storm with the naked eye. It appeared only after the rings were carefully separated and their carbon-14 content was measured. On the data curve, 1 point rose sharply above the surrounding years. The event on the sun became visible once again, not through light still traveling across space, but through an atom created by the atmosphere and preserved by a tree. This is a very different way for the past to survive. The history of the solar system is not found only in craters on the moon, in the rocks of planets, or in ancient light reaching telescopes. Part of that history also remains within living things that once existed very close to us. A tree can preserve rainfall, temperature, drought, and changes in the atmosphere. But in a few rare rings, its story extends beyond Earth. That layer of wood belongs not only to the forest, but also to the activity of the star that sustained the forest. The event more than 14,000 years ago is not a warning that a superstorm is certain to appear soon. The current record cannot tell us when a similar event will return, nor can it recover every characteristic of the ancient storm. What it shows is that the sun's range of activity extends beyond what several decades of satellite observations have recorded. The star usually provides the stable light and energy that sustain life, but at times it can also release particle streams far more powerful than anything the modern world has experienced. Today's society is more vulnerable than the communities that lived near the end of the Ice Age. Ancient people had no satellites, electrical grids, or navigation systems that could be disrupted. But neither could they observe the sun from multiple directions, issue warnings, or prepare shelters for people beyond Earth's atmosphere. The modern world depends more deeply on technology, but it also understands the danger more clearly. Telescopes watch active regions. Satellites measure particle streams. Solar wind observatories stand ahead of Earth, while forecasting centers continually send information to airlines, power utilities, and operators in space. Humanity cannot control the sun, but it can learn to live beside a star that is always in motion. A satellite can be placed into safe mode. Astronauts can move into shelter. Aircraft can leave polar routes, and electrical grids can reduce their loads before the strongest disturbances arrive. These measures do not create perfect protection, but they show that knowledge can turn a completely unexpected danger into a situation that has already been considered and prepared for. And part of that knowledge began in nature, not with an advanced instrument, but with trees that died long before humanity understood that the sun was a star. Nature preserved data in very quiet places, in ice, sediment, coral, and layers of wood only a few millimeters thick. These traces do not speak on their own. They simply wait until humanity has enough patience and the right tools to read them. Perhaps that is the gentlest part of the story of this enormous storm. An event powerful enough to cross space and alter the chemistry of the entire atmosphere was preserved inside something very small. Not through the sound of an explosion, but through a slightly different proportion of atoms within the wood of a distant spring. Every tree ring is 1 year of Earth. It tells of the light, water, and life that passed through it. But within a few rare rings, the memory of the planet also contains the memory of the sun. A thin line in wood survived longer than every story told about that day. And when humanity finally learned how to read it, the atmosphere of a world more than 14,000 years ago began to speak again.